The sun just did something terrifying. A vast hole ripped across its surface, unleashing a river of plasma at Earth. And at that exact moment, the interstellar visitor Comet 3I Atlas vanished from every telescope, and Mother Earth experienced an earthquake. Now the question on everybody's mind is what happened? Was it destroyed or transformed? And what might it look like when it re-emerges, if at all it will? As one comet slips into hiding, another bursts into the spotlight. Comet Lemon, an icy relic older than civilization itself, is racing across our skies. We tell you why the next 2 weeks are going to be crucial. Meanwhile, in China, physicists have achieved what sounds like pure science fiction, an unhackable communication network that is a total snitch. And don't blink, because before we close, we'll reveal the cosmic dates you cannot miss, including one no one is talking about, yet should. If these mysteries have you on edge the way they have me, don't just watch, take action. Hit like, smash subscribe, and stay locked in as these stories unfold in real time. Drop a comment with where you're watching from, what time it is there, and tell me straight. Do you believe we're being told the whole truth about these world-shifting discoveries? And if you want to help this community grow, share this video on X, Facebook, Reddit, or even your group chats. Every share, every comment, every click is fuel for the hunt. You're the reason we can keep chasing these stories. So, thank you for standing with us in the search. Part 1. The Disappearance. The sun just did something terrifying. October 2025 arrived with a cosmic alarm bell that most people never heard. Scientists monitoring our star watched in growing unease as a massive transquatorial coronal hole ripped open across the solar surface. A gash in the sun's magnetic field that looked like a wound bleeding invisible energy into space. This wasn't your typical solar activity, the kind that produces pretty auroras and maybe disrupts a few satellite signals. The hole was enormous, spanning regions of both the northern and southern solar hemispheres simultaneously. A configuration that happens rarely, and with consequences we're only beginning to understand. The solar wind that poured through this tear in the sun's magnetic armor reached speeds of 700 km/s. To put that in perspective, imagine a hurricane where every particle of air is moving at nearly 1.5 million mph. The stream of charged particles, protons, and electrons stripped from their atoms came screaming toward Earth like a cosmic fire hose aimed directly at our planet's magnetic field. The alignment was perfect, almost suspiciously so. The magnetic polarity of the solar wind matched Earth's field orientation in precisely the configuration needed for maximum coupling, the strongest possible transfer of energy from the sun's breath into our planetary magnetosphere. Geophysicists scrambled to predict the impacts. Power grid operators received warnings. Satellite controllers prepared for possible malfunctions. The aurora chasers packed their cameras and headed north, knowing this kind of solar assault would paint the sky in colors that defy description. But something else happened at that exact moment. Something that would turn this solar event from a routine space weather episode into a genuine cosmic mystery. Comet 3I Atlas, the second confirmed interstellar visitor ever detected in our solar system, disappeared behind the sun. One moment, it was there, a faint smudge of light moving on an orbit that originated in another star system, carrying ice and rock that formed in alien clouds around a sun we'll never see. The next moment, it vanished into the solar glare, swallowed by the overwhelming brightness of our star, rendered invisible to every telescope on Earth and in space. The timing was impossible to ignore, Earth's magnetic field getting hammered by the fastest solar wind in months, and simultaneously, our only accessible interstellar messenger going dark behind the very source of that assault. Scientists are careful, people trained to avoid jumping to conclusions conditioned to repeat the mantra that correlation does not equal causation. They measured their words carefully, when reporters asked if these events could be connected. Then, the earthquake started. Multiple magnitude 7 earthquakes struck different regions of Earth within hours of the solar wind's arrival. Seismometers recorded the violent shaking, the sudden release of tectonic energy that had been building for years, perhaps decades, in the stressed rock beneath our feet. The tremors were not unexpected in a statistical sense. Earth experiences roughly 15 magnitude 7 earthquakes every year on average, but having several occur in close temporal proximity to a major solar event and the disappearance of an interstellar comet triggered something in the human pattern recognition system, that ancient part of our brains that searches for connections that demands meaning from coincidence. Could the sun's magnetic assault on Earth have somehow triggered seismic activity? The mainstream scientific consensus says no, that's not how earthquake physics works. Tectonic plates don't care about magnetic fields or solar wind. They grind and slip according to the laws of rock mechanics and accumulated strain energy. But there are other voices, researchers working at the fringes of geophysics, who point to statistical anomalies in earthquake timing during solar maxima, who suggest mechanisms involving ionospheric coupling or subtle changes in Earth's rotation rate. These ideas haven't gained traction in peer-reviewed literature, but they circulate in conference hallways and online forums. Whispered possibilities that the mainstream hasn't yet disproven to everyone's satisfaction. The comet, though, that's where the real mystery lives. 3 Atlas earned its designation as the third confirmed interstellar object detected passing through our solar system. The first was 1I Oumuamua in 2017. That bizarre, elongated thing that tumbled through the inner solar system and exhibited acceleration that couldn't be fully explained by normal comet outgassing. The second was 2I Boris in 2019, which looked and behaved more like the comets we're familiar with, a reassuring ball of ice and dust that followed predictable physics. 3 Atlas was discovered in 2025, tracked as it fell toward the sun on a hyperbolic orbit, moving too fast to be bound by our star's gravity. Clearly, a visitor just passing through on its way back to interstellar space. These objects are incredibly precious to science. They're the only samples we have of material from other stellar systems, at least until we develop the technology to send probes to nearby stars and return with physical specimens, something that won't happen in any of our lifetimes. Every photon of the light we collect from an interstellar comet carries information about chemistry, about the composition of protoplanetary disks around other suns, about whether the processes that formed our solar system are universal or unique. When 3I Atlas disappeared behind the sun, we lost our ability to gather that data, at least temporarily. The question that haunts astronomers now is simpler and more disturbing than any of the speculation about solar, wind, or earthquakes. When 3 Atlas emerges from behind the sun, if it emerges at all, will we recognize what comes out? Did the sun just eat our interstellar visitor? Could the intense heat and radiation and magnetic turbulence near our star have reshaped it, broken it apart, vaporized it entirely? We're about to find out, and the answer might upend everything we think we know about these alien wanderers. Part 2. The Traveler. We lost. The story of 3 Atlas begins like most comet discoveries do, with patients with automated telescopes scanning the sky night after night, looking for anything that moves against the background stars. The ATLAS survey, short for Asteroid Terrestrial Impact Lust Alert System, consists of 4 robotic telescopes distributed around the globe, designed primarily to spot asteroids that might pose a collision threat to Earth. But the telescopes don't discriminate. They capture anything that moves, including comets. And in the early months of 2025, they captured something extraordinary. The object appeared first as a faint streak in images from the Hawaiian stations. Follow-up observations from other facilities confirmed it was moving and moving fast. Trajectory calculations revealed the telltale signature of a hyperbolic orbit, an eccentricity greater than 1, meaning this thing wasn't bound to the sun. It came from somewhere else, and after its close approach to our star, it would leave, headed back into the cosmic ocean between stars. The orbital energy was wrong for a solar system native. This was interstellar. The astronomy community mobilized quickly. Telescope time, always scarce and competed for months in advance, was suddenly made available. Spectroscopy, the analysis of the light reflected or emitted by the comet, became the priority. What was this thing made of? Did it contain the same mix of water ice, carbon dioxide ice, and organic molecules that characterize comets born in our solar system? Or would its composition reveal alien chemistry, ratios of elements that pointed to formation conditions around a different type of star? Early data suggested something puzzling. The brightness of 3 Atlas didn't behave quite like astronomers expected. Comets typically brighten as they approach the sun, following a predictable curve related to the increasing sublimation of ice. As solar heating intensifies, water ice starts subliming, turning directly from solid to gas when sunlight warms the surface to around 200 degrees Kelvin. Other volatiles like carbon monoxide and carbon dioxide sublimate at even lower temperatures, creating activity at much greater distances from the sun. The brightness curve of 3 Atlas showed flattening periods where the comet didn't brighten as much as models predicted, followed by sudden jumps in luminosity that suggested discrete outbursts of dust or gas. The coma, the fuzzy cloud of gas and dust surrounding the nucleus, appeared unusually faint in some observations. Dust production seemed lower than expected for a comet of its size. Some researchers speculated the nucleus might have an unusually high density, more rock than ice, which would explain the weak activity. Others suggested the opposite, that the nucleus was extremely porous, almost like a rubble pile held together by weak gravity, and that this structure was causing the ice to sublimate in unpredictable bursts rather than steadily. Then, there were the non-gravitational forces. Comets don't follow pure Keplerian orbits determined solely by the sun's gravity. When ice sublimates from the nucleus, it creates jets of gas that act like tiny rocket engines, pushing the comet slightly off its predicted path. These non-gravitational accelerations are small but measurable, and they introduce uncertainty into predictions of exactly where a comet will be at any given time. For 3I Atlas, these perturbations were particularly difficult to model. The orbit calculations kept getting refined, the error bars kept shifting, and astronomers grew increasingly uncertain about precisely when and where the comet would reappear from behind the sun. Some observations hinted at possible fragmentation before the disappearance. Comet nuclei are fragile things, weakly bound collections of ice and rock that can split apart under thermal stress or tidal forces. When a comet fragments, it often creates a train of smaller pieces following similar orbits, sometimes visible as multiple condensations in the coma. Imaging of 3 Atlas showed possible asymmetries, elongations that might indicate the nucleus was beginning to come apart. If the comet was already fragmenting before it disappeared, the question becomes even more pressing. What will emerge from the solar glare might not be a single object, but a stream of debris, or perhaps nothing at all if the fragments became too small to detect. The comparison to previous interstellar visitors was inevitable. One IUMA-MUA that first detected interstellar object was never confirmed to be a comet. It showed no visible coma, no dust tail, nothing that would definitively identify it as an icy body. Yet, it accelerated away from the sun in a manner that couldn't be explained by gravitational forces alone. The most likely explanation remained comet outgassing, but of a volatile, more exotic than water, possibly carbon monoxide or molecular nitrogen, substances that would sublimate without producing visible dust. The alternative explanations, from light sails to alien probes, captured public imagination, but found little support among scientists who deal in evidence rather than speculation. 2. Ice Brusso behaved more like a familiar comet with a proper coma and tail and brightness variations that match standard comet models reasonably well. Its spectrum revealed water vapor and carbon monoxide, chemistry similar to what we see in solar system comets. This was reassuring in a way. It suggested that planetary formation around other stars follows similar rules, produces similar objects. But Boris also showed signs of fragmentation near perihelion, its closest approach to the Sun. Images captured what appeared to be a small chunk breaking away from the main nucleus, a reminder that these interstellar travelers don't always survive their passage through the inner solar system intact. Now, 3 Atlas was following a similar path, diving toward the Sun, and we'd lost sight of it at the worst possible moment. The geometry of solar conjunction, when an object passes behind the Sun, as seen from Earth, creates an observation gap that can last days or weeks, depending on the object's trajectory and brightness. For a faint comet already showing signs of unusual behavior, this gap becomes a black box, a period where anything could happen and we'd have no way to know. The comet could be disintegrating. It could be brightening dramatically. It could be intact and simply too close to the Sun's glare to see. We wouldn't know until it emerged, if it emerged. Models attempted to predict what would happen based on assumed nuclear sizes and compositions. If the nucleus was large and mostly rocky, thermal models suggested it would survive with minimal mass loss. If it was small and icy, the heat near perihelion could vaporize it completely, leaving nothing but a dispersing cloud of gas and dust. The uncertainty in nucleus size was enormous, ranging from a few hundred meters to several kilometers, a factor of 10 or more. And that uncertainty propagated through every prediction model, turning forecasts into guesswork. The phrase astronomers kept using was invisible interstellar traveler, somewhere behind the Sun's glare, hidden from every telescope humanity has built. An object from another star system was either surviving or dying, and we could do nothing but wait and wonder what would emerge when the geometry finally allowed observation again. The wait felt like an eternity compressed into days. Part 3. When solar wind meets alien ice. The Sun is not a gentle thing. We think of it as our benign, life-giving star, the warm light that makes Earth habitable. But up close, the Sun is violent, chaotic, a roaring ball of plasma where temperatures reach millions of degrees and magnetic fields twist into configurations that store energy like loaded springs. When those springs snap, the results can be catastrophic for anything nearby. The coronal hole that opened in October 2025 was one of those events that makes solar physicists nervous. Coronal holes are regions where the Sun's magnetic field opens up into space rather than looping back to the surface. These open field lines act like highways for solar wind, allowing plasma to escape into the solar system at high speed. A typical solar wind speed is around 400 km/s. The wind pouring from this particular coronal hole was moving at 700 km/s, nearly twice as fast, carrying more momentum, more energy, more potential for disruption. When solar wind at those speeds encounters a comet, the interaction becomes complex and violent. Comets are not magnetically shielded like Earth. They don't have a magnetosphere to deflect the charged particles. Instead, the solar wind slams directly into the coma. The cloud of gas and dust surrounding the nucleus and strange physics takes over. The gas in the coma becomes ionized by solar ultraviolet radiation, creating a population of electrically charged molecules. These ions respond to magnetic fields, and the solar wind carries frozen in magnetic field lines that drape around the comet like a cape. The result is a magnetotail, a structure formed by the interaction between the solar wind's magnetic field and the ionized gas from the comet. This tail can extend millions of kilometers downstream away from the Sun, glowing faintly in the light of ionized carbon monoxide and other molecules. The tail is not a passive structure. Turbulence in the solar wind causes the tail to wave and flutter. Disconnection events can occur where the tail breaks off entirely, and a new one begins to form. These interactions are visible from Earth with the right instruments, and they provide clues about both the solar wind conditions and the comet's gas production rate. But what happens when a comet encounters an exceptionally fast solar wind while already stressed by intense solar heating near perihelion? History provides some terrifying examples. Cometon, discovered in 2012 and predicted to become spectacularly bright, disintegrated during its close pass by the Sun in 2013. Images from solar observing spacecraft showed the comet entering the perihelion region as a bright object and emerging as nothing but a dispersing cloud of dust. The nucleus apparently broke apart completely. Unable to withstand the thermal and tidal stresses, Comet Lovejoy, a sun grazer that passed within 140,000 km of the solar surface in 2011, somehow survived despite predictions it would be destroyed. Images captured the comet's tail extending millions of kilometers after perihelion, fed by massive gas production from the superheated nucleus. The survival of Lovejoy was unexpected and still not fully explained. Some combination of nuclear size, composition, and structural strength allowed it to endure heating that should have vaporized it entirely. 30. Atlas was not passing as close to the Sun as those extreme sun grazes, but it was entering the region where solar influence becomes dominant, and it was doing so during a period of unusually intense solar wind. The question became whether the combination of factors, thermal stress, plus radiative heating, plus solar wind pressure, plus possible prior fragmentation, would be enough to destroy it. Some researchers proposed more exotic interactions. The electric comet model promoted by a small group of plasma physicists suggests that comets develop electrical charges as they interact with the solar wind, and that electrical forces, not just thermal sublimation, drive comet activity. Mainstream astronomy has not embraced this model, finding that conventional physics explains observations adequately without invoking electrical effects. But proponents point to phenomena like disconnection events in comet tails and rapid brightness changes as evidence that electrical processes play a role. The hypothesis extends further into fringe territory, with suggestions that strong solar wind events could induce charge separations in a comet's coma that might, under certain circumstances, cause explosive disruptions or trajectory changes beyond what's expected from simple outgassing. The validation for these assertions is debated. The overarching theory remains incomplete, yet the concepts persist because they endeavor to elucidate observations that deviate from established models. When 3 Atlas vanished during a significant solar wind event, proponents of electric comet theories perceived this as potential substantiation of their hypotheses. Mainstream astrophysicists, however, interpreted it as an unfortunate, albeit coincidental, confluence of occurrences. Compounding the uncertainty is our incomplete understanding of 3 Atlas's composition. Spectroscopic examinations prior to its disappearance were limited and failed to furnish a comprehensive inventory of its constituent elements. The celestial body could be predominantly water ice, akin to many comets within our solar system. Alternatively, it might be rich in carbon monoxide ice, which vaporizes at considerably lower temperatures, potentially driving activity further from the Sun. It might also possess a high silicate content and be deficient in volatiles, resembling an asteroid more than a typical comet. Each of these compositions would react differently to solar heating and interactions with the solar wind. If the nucleus is exceptionally porous, resembling aerogel with a density barely exceeding that of the surrounding coma's gas, thermal waves could penetrate deeply, warming subsurface ice and potentially causing the entire structure to fragment through widespread sublimation. Conversely, if the nucleus is shielded by a dust mantle covering most of its surface, gas production would be confined to a few active zones, generating jets capable of inducing rotational instability or unpredictable torques. Should the nucleus be a contact binary, 2 lobes held together by weak gravitational forces, tidal stresses and thermal strain could lead to its fragmentation. In this context, the Sun acts as a cosmic arbiter, a destructive agent that scrutinizes every object traversing the inner solar system. Interstellar comets, originating from different environmental conditions and possibly possessing distinct structural characteristics from those within our solar system, might be especially susceptible, or, conversely, more resilient, having been forged in conditions that imparted greater toughness. We will not know until we witness its reappearance. The parallel with Comet Shoemaker-Levy 9 is illuminating. That comet was fractured by tidal forces during a close passage by Jupiter in 1992, breaking into over 20 fragments that subsequently impacted the planet in a dramatic sequence of collisions. The tidal disruption occurred because Jupiter's gravitational gradient across the comet's diameter surpassed its own self-gravity, effectively tearing it apart. The Sun's tidal forces are considerably weaker at the distance at which 3 Atlas passed. However, a comet already weakened by thermal stress or prior fragmentation could succumb to forces that a robust nucleus would readily withstand. Did the Sun just reveal something alarming about cosmic visitors from beyond our system? The answer hinges on what we observe when the comet re-emerges from conjunction. If 3 Atlas reappears intact, continuing its hyperbolic trajectory with normal gas and dust emissions, the solar wind event will be relegated to a footnote, a coincidence that fueled speculation but ultimately held no profound significance. If, however, the comet has disintegrated or vanished, we are left with perplexing questions about whether extraterrestrial objects are inherently more fragile than our current models suggest, or if their formation or internal structure renders them susceptible to solar influence in unforeseen ways. Part 4. The vigil commences. Astrophysicists are meticulously noting dates, verifying ephemerides, and devising observation strategies for the moment 3 Atlas is expected to become visible again. The timing is contingent upon several factors, including the comet's precise trajectory, which is subject to uncertainty due to non-gravitational forces, its brightness, which may have undergone significant alterations, and the observational geometry, which dictates how far from the Sun the comet must be before telescopes can detect it against the background sky. Current projections indicate that the comet should emerge from solar conjunction in late October or early November of 2025, achieving sufficient solar elongation, the angular separation from the Sun as viewed from Earth, to be observed by specialized instruments. Initial recovery efforts will likely involve space-based observatories, which are better equipped to obscure the Sun's glare than terrestrial telescopes. The Solar and Heliospheric Observatory, for instance, employs coronagraphs designed to create artificial eclipses, facilitating observation of the region near the Sun where comets often reside. STEREO, the Solar Terrestrial Relations Observatory, comprising 2 spacecraft in solar orbit, offers varied vantage points that might detect the comet earlier than Earth-based observations. The Parker Solar Probe, humanity's most intimate encounter with the Sun, follows an orbit that periodically brings it within Mercury's orbit, traversing regions where solar wind speed and temperature reach extreme levels. Should the probe's trajectory have brought it into proximity with 3 Atlas during the conjunction period, its instruments might have recorded data about the comet under conditions inaccessible to Earth-bound telescopes. However, Parker's primary scientific objectives are focused on the solar corona and solar wind, not comets. Consequently, unless the comet fortuitously intersected the probe's narrow field of view at the opportune moment, no data from this crucial interval will be available. Mission scientists have not reported any such serendipitous encounters, suggesting that the geometric alignment was unfavorable or that the comet was too faint for Parker's instruments to discern against the brilliant solar backdrop. What will the initial recovery images reveal? In the most optimistic scenario, the comet will appear as anticipated, perhaps slightly dimmer due to dust expulsion, but otherwise intact, exhibiting a visible coma and tail, indicative of active ice sublimation from the nucleus. Its spectral signature would display familiar emission lines of water vapor cyanogen, and carbon monoxide, the molecular fingerprints confirming its composition. The tail's length and structure would offer insights into the rate of gas production and solar wind conditions in the post-conjunction phase. Astronomers would quantify its brightness, compare it to pre-conjunction values, and assess whether the comet experienced significant mass loss during its closest solar passage. In the most pessimistic scenario, nothing will be observed. The sky will remain devoid of activity where 3 Atlas should be, suggesting complete disintegration. The nucleus may have fragmented into pieces too small to be individually detected, or may have vaporized entirely, leaving behind only a dispersed cloud of gas too diffuse to be recognized as a distinct object. While scientifically disappointing, this outcome is not unprecedented. Several comets have vanished following close solar approaches, and their loss contributes valuable data to our understanding of cometary fragmentation dynamics. Between these extremes lie numerous possibilities. The comet could reappear as a collection of fragments, a trail of condensations along its orbit indicating that the nucleus split, but the pieces survived. Observing fragment streams presents challenges, as each individual piece is fainter than the original nucleus, but they provide significant information regarding nuclear structure and the mechanics of fragmentation. If 3 Atlas returns as fragments, analysts will meticulously measure their separation distances and velocities to reconstruct the timing and mechanism of the breakup. Another possibility is dormancy. The comet might have depleted its near-surface volatiles during its close solar passage, leaving behind a desiccated crust that inhibits further sublimation until solar heating cracks the crust or erosion exposes fresh ice. Dormant comets resemble asteroids, exhibiting no coma or tail, merely a rocky surface reflecting sunlight. If 3 Atlas enters a dormant state, our ability to study its gaseous composition will be lost, but we will gain insights into surface processes and the formation of insulating mantles. The most intriguing scenario involves an unexpected surge in brightness. Comets sometimes fragment in ways that expose fresh, volatile-rich material to sunlight, triggering sudden increases in gas production and luminosity. A fragmenting nucleus can create new active regions, expanding the total sublimating surface area. If 3 Atlas fragments and brightens concurrently, the comet that emerges might be even more spectacular than the one that disappeared. However, in its fragmented state, it would likely diminish rapidly as the smaller pieces exhaust their ice reserves. Spectroscopic analysis will be paramount. Observations prior to conjunction revealed the characteristic signatures of water and possibly carbon monoxide, but a comprehensive spectral inventory was never obtained. Post-conjunction spectroscopy might identify species not detected previously, either because the comet was not producing them in substantial quantities or because our observations were not tuned to the appropriate wavelengths. Oxygen emission lines would signify water sublimation. Cyanogen, CN, points to carbon-nitrogen chemistry. Sodium and iron lines, occasionally observed in comets, can indicate the exposure of metallic-rich material from the nucleus's interior. Amateur astronomers can play a vital role in the recovery effort. A globally distributed network of backyard telescopes provides continuous sky coverage that professional facilities, with their limited observing time and scheduled programs, cannot match. If 3 Atlas brightens unexpectedly or fragments into widely separated pieces, amateur observers may be the first to notice. Crowdsourced astronomy has become increasingly significant as digital cameras and sophisticated software enable dedicated amateurs to produce observations comparable to professional quality. A cosmic mystery is unfolding in real time, and anyone with a telescope and clear skies can participate. The comet could reappear at any moment, assuming it has survived. Alternatively, days, then weeks, could pass with nothing visible until astronomers reluctantly conclude that 3 Atlas is gone, destroyed by the sun it traveled so far to visit. The pervasive uncertainty is both maddening and exhilarating. We dispatched no probe to intercept the comet. We have no means of actively searching for it beyond directing our telescopes towards its predicted location and waiting. Our sole recourse is to observe, to speculate, and to prepare for whatever emerges from the solar glare. The broader question continues to preoccupy the astronomical community. If the nucleus is no more, does 3 Atlas still exist? Or is it merely debris now, a dispersed cloud of gas and dust that was once an interstellar comet, but no longer qualifies as a discrete celestial object? Philosophically, this echoes the ship of Theseus paradox. If every plank of a wooden ship is replaced over time, is it still the same vessel? If a comet fragments into 1,000 pieces, each following a nearly identical orbit and carrying material from the original nucleus, are they collectively still the comet, or has the comet ceased to exist? There is no formal definition to resolve this query. It is a matter of convention and practicality, and different researchers will offer differing perspectives. However, the question carries weight, because 3 Atlas represents something precious and irretrievable, a sample from another star system. Its loss feels like more than just the disappearance of an astronomical target. It feels like the severing of a connection to something vast and distant, a link to the wider galaxy that was broken before we could fully comprehend what we held. Part 5. When coincidence morphs into conspiracy. Why does any of this matter beyond the confined domains of planetary science journals and astronomical conferences? Because humans are inherently pattern-seeking beings, evolved to discern meaning in correlations and to perceive connections where none may exist. The simultaneous occurrence of a major solar event, the disappearance of an interstellar comet, and multiple significant seismic events on Earth has triggered primal alarms within our collective consciousness, screaming that something extraordinary is unfolding. The prevailing scientific stance regarding connections between solar activity and terrestrial earthquakes is unequivocal. Earthquakes are primarily caused by plate tectonics, the slow, inexorable movement of lithospheric plates on the convecting mantle, and the accumulation of strain energy in the Earth's crust that eventually overcomes the frictional resistance locking faults. Solar activity lacks any plausible mechanism to instigate such a release. Magnetic fields do not influence rock, and solar wind particles do not penetrate to Earth's surface, being deflected by the magnetosphere and atmosphere. The thermal energy imparted by solar radiation is negligible compared to Earth's internal heat. Every analysis of earthquake catalogs, searching for correlations with solar cycles or individual solar events, has yielded no results beyond what would be anticipated by chance. Nevertheless, correlations continue to appear in datasets, presenting tantalizing patterns that fall just short of statistical significance, but do not entirely vanish. Some researchers operating on the periphery of scientific respectability persist in investigating potential mechanisms. Could ionospheric disturbances, induced by solar activity, influence the electrical properties of fault zones? Could subtle alterations in Earth's rotation rate or magnetic field orientation, driven by solar wind momentum transfer, modulate tectonic stress at levels too minute for direct measurement, but sufficient to tip a fault already nearing failure? Is there a magneto-hydrodynamic coupling between the ionosphere and conductive layers within the crust that transmits energy in ways we have yet to comprehend? These hypotheses encounter substantial skepticism because extraordinary claims demand extraordinary evidence, and the existing evidence remains circumstantial at best. However, the human mind does not operate solely on statistical significance thresholds. It functions through narrative, constructing stories that weave disparate events into cohesive wholes. When the sun unleashes its fury, earthquakes strike, and a comet vanishes, all within the same news cycle, the narrative writes itself, even if the underlying physics does not support it. The interstellar nature of 3 Atlas introduces another layer of mystery and conjecture. These objects originate from beyond our solar system, from environments we can barely envision, formed from materials whose composition and isotopic ratios might differ from terrestrial norms. They are, in the most precise sense of the word, alien. Humanity has consistently projected its hopes and fears onto the alien and the unknown. When Oumuamua exhibited acceleration inexplicable by standard cometary outgassing, speculation arose regarding artificial origins, extraterrestrial probes conducting reconnaissance, or technologies beyond our comprehension. The most straightforward explanation remained natural processes, yet the alien probe hypothesis captured public imagination because it fulfilled narrative needs that dry scientific papers on carbon monoxide sublimation could never satisfy. 3. Atlas disappearing during a solar storm invites similar conjecture. Did the comet carry something, conceal something, that designated it a target? Are we witnessing a cosmic quarantine protocol, with the sun neutralizing potential threats from interstellar space before they can penetrate the inner solar system? The scientific implausibility of these notions does not diminish their psychological allure. We desire the universe to harbor mysteries deeper than orbital mechanics and spectroscopy. We seek hidden meanings behind celestial alignments. We wish for comets to be more than merely dirty snowballs. We want them to be messengers, conduits of information, life, or purpose. The hypothesis of panspermia, the idea that life disseminates throughout the cosmos via comets and asteroids, lends a scientific veneer to these desires. If comets delivered the organic precursors that initiated life on Earth during the period of heavy bombardment billions of years ago, then every comet becomes a potential seed carrier, and interstellar comets gain particular significance as they might carry chemistry from biospheres orbiting other stars. The destruction of 3 Atlas, if indeed it occurred, then signifies the obliteration of a biological sample, a library consumed before its contents could be deciphered. More esoteric possibilities circulate within fringe communities. Proponents of the electric universe model perceive the sun's interaction with the comet as evidence of plasma physics, which they contend mainstream science ignores. They point to the comet's unusual brightness fluctuations, the intense solar wind, and disconnection events observed in other cometary phenomena, arguing that these occurrences necessitate electrical, rather than gravitational and thermal, explanations. The mathematical rigor of their models rarely withstands scrutiny, and their predictions frequently fail to align with observations. However, the intuitive appeal of electricity as a universal force, coupled with the visual drama of lightning and sparks, imbues electric universe concepts with a persistence that transcends their scientific shortcomings. Conspiracies inevitably arise. Are space agencies withholding data from the Parker Solar Probe's close solar passes? Did instruments capture images or spectral data of 3 Atlas during the conjunction period that officials chose not to disclose? What could motivate such secrecy? Perhaps the comet exhibited behavior that defied explanation, challenged fundamental assumptions, or instilled fear in those who grasped the implications. It might have fragmented in a manner inconsistent with natural processes, or emitted signals, or altered its trajectory in ways suggesting deliberate control. These scenarios are exceedingly improbable, bordering on the impossible. Yet, in minds predisposed to distrust official narratives, the absence of evidence becomes evidence of conspiracy. The psychological function of conspiracy theories is well documented. They offer a sense of control, or the illusion thereof, in the face of random and chaotic events. They replace a universe characterized by meaningless coincidence with one of hidden order and purpose, even if that purpose is malevolent. It is preferable to believe in conspiracies than to accept that earthquakes occur randomly, that comets disintegrate without reason, and that we are merely tiny consciousnesses adrift on a fragile world hurtling through an indifferent cosmos. The narrative of concealed knowledge and suppressed truths is emotionally more gratifying than that of patient scientific investigation, slowly converging on tentative conclusions. However, there is a crucial point. Sometimes the universe does align in ways that defy probability. Occasionally, coincidences are so striking that they demand attention, even when causation cannot be established. The October 2025 convergence of events, the solar storm, the comet's disappearance, and the earthquakes, might be precisely such a case, a coincidence so improbable that it warrants our focus, even if ultimately it signifies nothing. Or it could be the initial indication of connections we have yet to comprehend, subtle couplings between geophysical systems and space weather operating below our current detection thresholds. Science advances by investigating anomalies, not by dismissing them. The researchers exploring solar earthquake correlations are engaged in legitimate, albeit speculative, scientific inquiry. They will likely find nothing definitive, but the search itself holds inherent value. When 3 Atlas emerges from behind the sun, if it does emerge, we may not recognize it. The comet that entered conjunction might not be the same entity that emerges. And when astronomers publish their analyses of their observations, presenting explanations grounded in physics, chemistry, and orbital mechanics, some individuals will accept these explanations and move forward. Others will continue to seek hidden meanings, connections between the comet, the earthquakes, and the solar storm that transcend material causation. Both responses are fundamentally human. Both reflect profound needs to make sense of our place in a cosmos that offers more questions than answers. The sun enacted something terrifying. A comet vanished, the earth trembled, and whatever underlying truth governs these events, we are left with a profound sense of wonder and unease. Part 6. The Visible Comet. While the Comet 3 Atlas is playing a game of hide-and-seek behind the sun, another celestial visitor is putting on a display that's readily observable, provided you know precisely where to direct your gaze and are willing to sacrifice some sleep, either by rising before dawn or staying up past twilight. Comet C 2025A6, identified by the Mount Lemmon Observatory in Arizona and consequently bearing the designation Lemmon, is currently making its way toward its closest encounter with the sun. It's reaching luminosity levels that render it visible through binoculars or modest telescopes, and under exceptionally dark skies, far from the glare of urban lights, it might even be perceptible to the unaided eye. The upcoming 2 weeks represent the prime period for observation. Lemmon's closest approach to the sun, known as perihelion, is slated for the middle of November in the year 2025. However, due to the configuration of its orbit, it achieves its maximum visibility from Earth slightly preceding this point, when it remains sufficiently distant from the sun's dazzling rays for comfortable viewing. Presently, the comet graces the pre-dawn eastern sky, ascending a few hours before sunrise and emitting a soft, hazy radiance characteristic of an active comet possessing a well-formed coma and, potentially, a developing tail. Current projections for its magnitude place Lemmon between 4 and 5, right at the cusp of naked-eye visibility. Under ideal conditions, the human eye can generally discern objects down to magnitude 6. A magnitude 4 object should be readily apparent away from city illumination, though pinpointing it without optical aid necessitates knowing its exact celestial coordinates. The comet is presently traversing the constellation Cancer, progressing eastward against the backdrop of fixed stars. Charts detailing its path, readily accessible online, illustrate its trajectory relative to familiar star formations. Observing comets demands both patience and access to clear, dark skies. Unlike planets, which appear as sharp points or disks, comets are diffuse entities, their light spread over a broader area. This inherent diffuseness makes them more susceptible to light pollution and atmospheric conditions than compact objects of comparable integrated brightness. A comet of magnitude 4, will effectively vanish in the bright skies of a suburban environment where stars of the same magnitude remain easily visible. Success hinges on venturing away from populated areas to locales where the Milky Way is clearly visible overhead, and where the sky's profound darkness allows one's eyes to detect faint, extended objects with low surface brightness. Binoculars stand out as the ideal instrument for comet observation. They provide sufficient magnification to concentrate the comet's light while maintaining a wide field of view, simplifying the process of locating and tracking the object. 7x50 binoculars, a common size among amateur astronomers and nature enthusiasts, prove particularly effective. Mounting them on a tripod, if feasible, will mitigate hand tremor and allow for extended viewing sessions without inducing fatigue. The comet will likely present itself as a small, hazy patch, distinctly non-stellar in appearance, possibly exhibiting a subtle greenish hue derived from the emission of diatomic carbon molecules within its coma. Telescopes can unveil finer details, revealing the structure of the coma, any jets or fans of material erupting from specific active regions on the nucleus, and the tail, should it have developed sufficiently. However, increased magnification constricts the field of view, making the comet more challenging to locate initially and to keep centered as Earth's rotation shifts its apparent position across the sky. Many seasoned comet watchers favor binoculars for their aesthetic appeal. The expansive field of view allows the comet to be appreciated within the context of the surrounding star fields in the Milky Way, underscoring its role as a transient visitor moving through a more enduring celestial panorama. Early observations of Lemon have revealed a phenomenon that simultaneously excites and concerns comet scientists. Its brightness has not adhered precisely to prediction models. Predicting cometary brightness is a notoriously complex endeavor, as it depends on factors that are not directly measurable, such as the nucleus's size, composition, rotational state, surface characteristics, and the ratio of dust to gas. Models rely on statistical assumptions derived from other comets, but individual objects frequently deviate from these averages. Lemon has exhibited periods of unexpectedly rapid brightening, followed by plateaus where its luminosity remained nearly constant despite its decreasing proximity to the Sun. These anomalies could signify several processes. Outburst activity, wherein the sudden exposure of fresh volatile materials leads to a temporary surge in gas and dust production, can trigger rapid brightening. Rotational variations of the nucleus, if one hemisphere is significantly more active than the other, can lead to periodic fluctuations in brightness as different sides are illuminated by the Sun. More troublingly, these deviations might herald the initial stages of fragmentation, where the nucleus begins to fracture under thermal or tidal stress. Fragmentation represents the latent peril that perpetually shadows every comet prediction. A comet can brighten steadily, following its anticipated trajectory toward perihelion, appearing healthy in every regard, only to suddenly begin disintegrating. This process can unfold rapidly or gradually. At times, a substantial fragment may break away, forming a distinct luminous condensation adjacent to the main nucleus. In other instances, the entire nucleus may disintegrate into a diffuse cloud of minuscule fragments, individually too faint to discern, but collectively capable of producing a remarkable increase in overall brightness as their aggregated surface area fuels enhanced sublimation. The physics governing fragmentation involves mechanical strength, thermal stress, and rotational dynamics. Comet nuclei are inherently weak structures, more akin to compacted snow than solid rock, held together primarily by their own minimal gravitational pull, augmented by the tensile strength of ice and possibly organic tars. As the Sun heats one hemisphere of the nucleus, thermal expansion generates internal stress. If the nucleus is rotating, centrifugal forces introduce additional mechanical stress, and the expulsion of jets can impart torques, accelerating the nucleus's spin. At a certain threshold, The accumulated stress surpasses the material's inherent strength, causing cracks to propagate and the nucleus to fracture. The sublimation science governing Lemon introduces another layer of intricacy. The comet appears to be driven by the sublimation of carbon monoxide or carbon dioxide to a degree comparable to, or even exceeding, that of water. These molecules are more volatile than water, meaning they transition from solid to gas at lower temperatures and at greater distances from the sun. A comet propelled by carbon monoxide can remain active far beyond the traditional snowline, where water ice would remain frozen, producing a coma and tail while still situated in the outer reaches of the solar system. As the comet draws nearer to perihelion and temperatures escalate, water sublimation eventually assumes prominence, often triggering a shift in activity patterns and luminosity behavior. The interaction of the tail with the solar wind presents an additional avenue for observation. Lemon's ion tail, should one develop, will invariably point directly away from the sun, propelled by the solar wind much like a windsock. The dust tail, by contrast, follows a curved trajectory. Particles are propelled by solar radiation pressure, but retain the orbital momentum they possessed at the moment of their release from the nucleus. These two distinct tail types, the ion and the dust tail, frequently separate into observable structures in photographic records. The ion tail exhibits a bluish tint resulting from the emission of carbon monoxide ions and typically appears straight, occasionally displaying streamers and knots influenced by irregularities in the solar wind's magnetic field. The dust tail, reflecting sunlight, presents as yellowish-white, broader and more diffuse, curving gently away from the nucleus. A comparison between Lemon and 3 Atlas highlights fundamental distinctions between comets indigenous to our solar system and those originating from interstellar space. Lemon coalesced some 4.6 billion years ago within the disk of gas and dust that surrounded the nascent sun, likely in the region beyond Neptune, where temperatures were sufficiently low for water and other volatile compounds to condense into ice. Gravitational disturbances orchestrated by the giant planets eventually scattered it into the Oort cloud, that vast spherical reservoir of comets encircling the solar system at distances extending up to 100,000 astronomical units. Some perturbation, perhaps the gravitational influence of a passing star or a colossal molecular cloud, altered Lemon's orbit, initiating its descent back toward the sun on the very journey we are now observing. Its composition serves as a repository of primordial solar system chemistry, reflecting the isotopic ratios and molecular abundances prevalent in our local galactic sector 4 billion years ago. 3 Atlas, conversely, formed elsewhere, orbiting a different star under conditions that might have been either remarkably similar or drastically divergent. The temperature and pressure within that protostellar disk, the abundance of heavier elements, the prevailing radiation environment, and the timing of planetary formation all exert influence on a comet's composition and structure. By contrasting interstellar comets with those native to our solar system, we are essentially comparing samples drawn from different stellar nurseries, seeking commonalities that illuminate universal processes and divergences that underscore localized variations. Lemon serves as a potent, real-time testament to the inherent fragility of comets. Every comet embarks on a perilous journey, gambling against disintegration. The majority successfully navigate their perihelion passage, shedding some mass through sublimation, and retreat to the outer solar system or beyond, remaining intact. Others undergo dramatic fragmentation, staging spectacular celestial displays as multiple nuclei and expanding dust clouds surge in brightness before fading. A select few vanish entirely, obliterated so completely that their subsequent tracking becomes an impossibility. Witnessing Lemon during its peak visibility window transcends mere appreciation of a beautiful celestial spectacle. It is an encounter with a survivor, an entity that has endured billions of years in the frigid expanse of the Oort cloud and is now traversing a gauntlet of solar heat and radiation that may or may not culminate in its demise. The timing of this event is propitious. While 3 Atlas remains obscured behind the Sun, Lemon offers a substitute target, a different comet that we can actively observe and scrutinize. If you have never witnessed a comet firsthand, having encountered them solely through digital imagery or textbook diagrams, this presents your opportunity. Venture outdoors before dawn, seek out a location with minimal light pollution, allow your eyes approximately 10 to 15 minutes to adapt to the darkness, and systematically scan the eastern sky within the boundaries of Cancer. That faint, hazy patch of light, should you locate it, encapsulates ice that predates Earth's formation, organic molecules that predate life itself, and silicate dust older than our planet. You are beholding a messenger from the dawn of the solar system, and within 2 weeks, it will fade from view, its fleeting moment of visibility overshadowed by its predetermined destiny. Whether survival or disintegration remains unwritten. Observe the heavens now while Atlas remains hidden. Part 7. The Swan and the Context. Comets often appear in succession, or so it seems to those who track these icy wanderers. The reality, however, is more prosaic. At any given moment, a multitude of comets are in orbit around the Sun at varying distances, the vast majority too faint to be observed without substantial telescopic equipment. A select few possess sufficient brightness to capture the attention of amateur astronomers, and on very rare occasions, one becomes spectacular enough to be visible to the naked eye and capture the public imagination. The perceived clustering arises from observational biases and the statistical nature of comet discoveries, yet it still results in periods where comet watchers have multiple targets to choose from. The year 2025 is shaping up to be one such period. Alongside Lemon and the elusive 3I Atlas, another comet, designated C2025 R2 Swan, has been catalogued. The Swan designation refers to the solar wind anisotropies instrument aboard the SOHO spacecraft, which observes the sky in ultraviolet wavelengths particularly sensitive to hydrogen emission. Comets generate immense hydrogen clouds, formed from neutral hydrogen atoms created when water molecules dissociate under solar ultraviolet radiation. These clouds are invisible to optical telescopes but emit brightly at specific UV wavelengths, allowing SWAN to detect them from vast distances, sometimes identifying comets months before they become visible to ground-based observers. C2025 R2 Swan was initially discovered through its hydrogen corona, that immense, invisible envelope surrounding its visible coma. Subsequent optical observations confirmed the discovery and enabled trajectory calculations. The comet is following a highly elliptical orbit that will bring it to perihelion in early 2026, well after Lemon's close encounter, but soon enough to maintain sustained interest among comet observers as they prepare their equipment and refine their observation strategies. Preliminary brightness estimates for SWAN suggest it might reach a magnitude of 6 or 7 at perihelion, rendering it a binocular object but likely not visible to the naked eye, except under extraordinary circumstances. The predicted brightness is contingent upon assumptions regarding nucleus size and activity level, both of which remain subjects of uncertainty. Some comets detected by SWAN have surpassed expectations, exhibiting significant brightening as they approach the Sun. Others have proven disappointing, remaining faint and diffuse despite optimistic forecasts. The only definitive way to ascertain their true nature is through ongoing observation and patient waiting. One intriguing possibility associated with newly discovered comets involves meteor showers. As a comet approaches the Sun, it sheds dust particles that disperse along its orbital path, forming a trail of debris. Should Earth's orbit intersect this debris stream, the particles will impinge upon our atmosphere at high velocities, typically between 30 and 70 kilometers per second, vaporizing in brilliant streaks that we perceive as meteors or shooting stars. Most annual meteor showers, such as the Perseids in August or the Geminids in December, result from Earth traversing well-established dust trails deposited by comets that have completed multiple perihelion passages, leaving behind dust over centuries or millennia. Newly discovered comets undertaking their initial passage through the inner solar system can trigger unpredictable meteor activity. The dust distribution along their orbits has not yet been smoothed out by repeated passages and gravitational perturbations. Fresh outbursts might create dense clumps of particles, and if Earth happens to pass through one of these aggregations, meteor rates could surge dramatically, culminating in a meteor storm characterized by hundreds or even thousands of visible meteors per hour. Such events are infrequent and notoriously difficult to predict, as they depend on the precise spatial distribution of the dust, a factor that cannot be directly measured. Swan's orbit will be meticulously calculated in the coming months, and astronomers will determine whether any potential intersections with Earth's dust stream might occur. Even a low probability prospect of a meteor shower ignites enthusiasm among both comet and meteor enthusiasts. Witnessing a meteor storm is a quintessential bucket list experience, a celestial fireworks display that typically occurs perhaps once or twice per generation. The meteors appear to radiate from a specific point in the sky known as the radiant, where parallel particle trajectories entering the atmosphere converge due to perspective. During a storm, the entire sky seems to rain meteors, with streaks of light appearing in every direction, overwhelming the senses in a manner that photographs can never fully convey. However, for every comet that brightens and performs as anticipated, a multitude falter. The annals of cometary astronomy are replete with predictions that proved erroneous, with objects expected to become magnificent comets instead remaining faint and unremarkable. Comet Kahutek in 1973 was predicted to become one of the brightest comets of the century, but barely achieved naked-eye visibility, disappointing millions who had been promised a spectacular celestial show. Comet Lovejoy in 2013 was expected to survive its perihelion passage and brighten dramatically, but instead, it disintegrated. These instances of failure impart humility and serve as a potent reminder of how much remains unknown about cometary physics. The comparative analysis of Swan and Lemon's brightness curves will ultimately yield valuable scientific data. Observing two comets simultaneously under comparable solar conditions allows for a direct comparison of their activity levels and sublimation physics. Discrepancies in brightness at equivalent distances from the Sun indicate differences in nucleus size, composition, or surface properties. If one comet is predominantly water-driven and the other carbon monoxide-driven, their activity profiles will diverge in characteristic ways. If one fragments while the other remains intact, we gain insights into structural differences that dictate susceptibility to fragmentation. Employing Swan and Lemon as comparative foils introduces narrative tension. Many comets falter. Will 3i Atlas also fail? Is there something inherent in the current solar environment that diminishes the likelihood of cometary survival? The October 2025 coronal hole event, while potentially a singular anomaly, might signify a period of heightened solar activity that poses a threat to any comet transiting the inner solar system. The Sun's 11-year activity cycle is approaching its solar maximum, the phase characterized by frequent sunspots and coronal mass ejections, and increased solar wind speeds and magnetic field strengths. Comets approaching perihelion during solar maximum encounter more formidable conditions than those that arrive during solar minimum. The historical record of cometary fragmentation offers sobering statistics. The tidal disruption of Comet Shoemaker-Levy 9 by Jupiter in 1992, followed by its spectacular impacts in 1994, vividly demonstrated the profound extent to which a comet can be annihilated by gravitational and tidal forces. Comet 73P Schwarzmann-Bachmann 3 fragmented during its 1995 apparition, splitting into multiple pieces that progressively separated over subsequent years. By its 2011 return, The comet had fractured into over 60 identified fragments, forming a debris field extending over several thousand kilometers of its orbit. Some fragments continued to exhibit activity, producing small comas, while others appeared dormant, their volatile materials depleted or sealed beneath inert crusts. These fragmentation events carry significant implications for predicting potential space hazards. A single, large cometary nucleus presents a minimal risk to Earth, as the probability of such a nucleus, only a few kilometers in diameter, impacting our planet, is vanishingly small. However, a fragmenting comet generates dozens or hundreds of pieces, each with the potential for atmospheric entry. While these individual fragments are smaller and less destructive than the original nucleus, the probability of one of them intersecting Earth's path increases. Most cometary fragments burn up harmlessly in the atmosphere or miss Earth entirely, but the risk calculation shifts when dealing with dispersed debris rather than a singular object. The foreshadowing of the 2025 comet event, predicted to be the brightest cometary apparition of the century, provides a valuable perspective on current observations. Comets function as the solar system's chaotic chronometers, appearing unpredictably, brightening erratically, and fragmenting without warning. They mark time in human consciousness in a manner distinct from the regular celestial ballet of planets and stars. A generation remembers Halley's Comet in 1986, a somewhat disappointing viewing experience for most, but culturally significant nonetheless. The preceding generation recalls Comet Hale-Bopp in 1997, visible to the naked eye for months and bright enough to be seen even from urban centers. The current generation may remember Lemon, Swan, or Three-Eye Atlas, contingent upon their survival and sufficient brightening. Are we currently experiencing a period of unusual cometary appearances? Statistical analyses of comet discovery rates over decades reveal fluctuations that might indicate genuine clustering, or may simply be a reflection of advancements in detection technology. An increased number of telescopes scanning larger portions of the sky with heightened sensitivity naturally leads to the discovery of more comets. The Atlas survey, which discovered Three-Eye Atlas, is specifically designed to locate near-Earth objects and incidentally finds comets. The Catalina Sky Survey, the Mount Lemmon Observatory, and Pan-STARRS in Hawaii all employ automated systems that continuously monitor the skies for any moving objects. Comets, by their nature, move and are thus detected. However, there is a tantalizing hint within the data suggesting that the Oort cloud, that distant reservoir of comets, might experience perturbations that send showers of comets plummeting toward the inner solar system. These disturbances could be caused by passing stars, gravitational interactions with giant molecular clouds within the galaxy, or even the vertical oscillation of the solar system as it orbits the galactic center. Any of these phenomena could dislodge comets from their remote orbits. If these celestial events are actual, such meteor showers would manifest on timescales spanning millions of years, far exceeding the duration of direct human observation. However, embedded within the layers of geological history, indications of clustered impacts could potentially illuminate these ancient torrents of comets that once bombarded the inner reaches of our solar system during the era of the dinosaurs, or even at earlier junctures in Earth's past. Comets serve as the solar system's erratic chronometer, precisely because their trajectories deviate from the predictable, ordered paths followed by planets. Most planets traverse orbits that are nearly circular, allowing their positions to be calculated with remarkable accuracy centuries in advance. Comets, conversely, emerge from the distant void on highly elongated elliptical paths. Their return intervals, if they indeed return, can span decades, centuries, or millennia. Some represent novel arrivals, venturing for the first time from the Oort cloud's unfathomable depths. Others are short-period comets, ensnared by Jupiter's gravitational pull into orbits that bring them back within a few years. They serve as a potent reminder that our solar system is not a perfectly calibrated clockwork mechanism of flawless orbits, but rather a vibrant, unpredictable environment where gravitational forces continuously rearrange celestial courses and new celestial bodies enter the cosmic arena without prior notice. Part 8. The Indomitable Signal. While celestial observers meticulously scan the heavens for comets and monitor the solar wind, a different kind of cosmic competition unfolds within laboratories and at ground-based facilities here on our planet. In the year 2025, China proclaimed the completion of the world's longest quantum communication network, a sprawling system measuring 12,900 kilometers, linking Beijing with remote ground stations through satellite relays. The nation asserted that this network provides data transmission capabilities that are essentially unassailable. This announcement signifies a pivotal moment in the unfolding quantum information revolution. Furthermore, should this system perform as claimed, it possesses the capacity to fundamentally reshape the landscape of global communications and cybersecurity in ways that extend far beyond immediate military or commercial considerations. Quantum key distribution, the foundational technology behind this achievement, leverages the intrinsic properties of quantum mechanics to detect any attempts at eavesdropping. The fundamental principle is as elegant as it is peculiar. Information is encoded within the quantum states of photons, individual particles of light, which are then transmitted through optical fibers or across the void between satellites and ground stations. The quantum no-cloning theorem fundamentally ensures that these quantum states cannot be perfectly replicated. Any effort to measure or intercept these photons will invariably disturb them in ways that are detectable. Consequently, any two parties sharing a quantum communication channel can collaboratively generate encryption keys and ascertain with absolute certainty whether any unauthorized entity attempted to intercept those keys during their transmission. The process commences with entangled photons, pairs of particles generated simultaneously and bound by a quantum connection, such that measuring specific properties of one photon instantaneously influences the other, irrespective of the distance that separates them. This peculiar phenomenon, famously dubbed spooky action at a distance by Einstein, has been rigorously verified through countless experiments and forms the bedrock for numerous proposed quantum technologies, including quantum computing and quantum teleportation. In the context of quantum key distribution, entangled photons empower two parties to establish shared random numbers that can subsequently be employed as encryption keys. The hardware implementation demands extraordinary levels of precision. Photons must be generated, entangled, transmitted, and detected with minimal signal degradation and maximal accuracy. Optical systems must meticulously align satellite transceivers with ground stations separated by hundreds or thousands of kilometers, while simultaneously compensating for atmospheric disturbances, the movement of satellites, and the rotation of the Earth. Individual photon detectors must be capable of registering single particles arriving at rates of thousands or even millions per second, distinguishing genuine signals from background noise and spurious detector activations. Error correction protocols are essential to address inevitable imperfections while still upholding robust security. China's system relies on the Morning Star Initiative, MSI satellite, launched in 2016 and named in honor of an ancient Chinese philosopher. This satellite orbits at an approximate altitude of 500 kilometers, traversing over ground stations in a sun-synchronous orbit that provides consistent communication windows. During each pass, which lasts for several minutes, the satellite distributes entangled photons to pairs of ground stations, enabling them to establish shared encryption keys. These keys then serve to secure conventional data transmissions utilizing standard encryption algorithms, with the quantum channel providing the assurance that the keys themselves were not compromised. The recent expansion of this network to 12,900 kilometers represents a significant engineering feat. Earlier demonstrations were limited to shorter distances or depended on intermediate relay stations that theoretically could have been compromised. The newly established system links quantum connections across multiple satellite passes and ground stations, thereby establishing end-to-end security on a continental scale. According to Chinese researchers, this network is already being utilized by government and financial institutions, safeguarding their communications against both current and prospective decryption threats. This last point is of critical importance. Contemporary encryption systems, which currently protect everything from financial transactions to sensitive government communications, are predicated on mathematical problems that are exceedingly difficult for classical computers to solve. Examples include factoring large numbers or computing discrete logarithms. These tasks demand such an immense computational effort that breaking encryption becomes practically impossible, even with the most powerful supercomputers available. However, quantum computers, if developed to a sufficient scale, could readily solve these problems, rendering current encryption methods obsolete. Data that is encrypted today and intercepted by adversaries could potentially be decrypted years or even decades from now, once quantum computers mature. Quantum key distribution offers protection against this harvest now, decrypt later threat, as its security is not contingent upon computational complexity, but rather on the fundamental laws of physics. Western nations, particularly the United States and European countries, view China's advancements in quantum communications with considerable apprehension. The MIT Technology Review Quantum Index in 2025 positions China ahead in several quantum technology metrics, including quantum communications and quantum sensing. American research initiatives are actively striving to bridge this gap, with the Department of Energy providing funding for quantum network testbeds and the Defense Advanced Research Projects Agency, DARPA, exploring space-based quantum communication architectures. Nevertheless, China's early lead and substantial government investment have created a discernible quantum disparity that raises concerns among defense planners and technology strategists. The policy implications extend beyond mere technological competition. If quantum communication networks come to form the essential infrastructure for future secure communications, nations lacking access to this technology risk facing a significant disadvantage in information control. International agreements governing the development of quantum technology remain nascent. Questions pertaining to export controls, technology transfer, and standardization are still unresolved. Some researchers advocate for open collaboration and shared development of quantum networks as a global utility, analogous to the way the Internet evolved into an international resource. Others champion a strategy of competitive advantage and restricted access, viewing quantum superiority as an invaluable strategic asset not to be shared. Could space-based quantum networks indeed become the backbone of the future Internet? This vision entails vast constellations of quantum satellites providing worldwide coverage, ground stations situated in every major urban center, and quantum repeaters extending the range beyond the limitations of direct line of sight. Data would traverse these networks, encrypted by quantum keys that are continuously refreshed, rendering them immune to interception and resistant even to future technological advancements that we cannot yet conceive. The system would seamlessly integrate with existing fiber optic networks, establishing a hybrid classical quantum infrastructure where quantum channels distribute keys and classical channels handle the transmission of bulk data. Inevitably, conjectures and conspiracy theories arise surrounding technologies that are as advanced and as shrouded in secrecy as these systems. Quantum key distribution protocols necessitate extensive testing and calibration procedures, which generate substantial data concerning photon transmission statistics, detector efficiency, and error rates. A significant portion of this data is classified or proprietary. Chinese publications describe the system's capabilities in general terms, but omit crucial engineering specifics that would allow for independent verification or replication. Western intelligence agencies are undoubtedly scrutinizing this program closely, employing signals intelligence and other methodologies to assess its actual capabilities in comparison to public pronouncements. This lack of transparency fuels speculation regarding whether the system functions as advertised or if undisclosed vulnerabilities exist. Concerns are also voiced about the potential for state surveillance. A government controlling a nationwide quantum communication network would possess an unprecedented capacity to monitor who is communicating with whom, even if the content of those communications remains encrypted. Metadata, the information pertaining to communication patterns rather than their substance, often reveals as much as the messages themselves. Traffic analysis can effectively identify social networks, track movements, and predict behavior. A quantum network that meticulously logs every connection, every photon transmission, and every key generation event essentially creates a surveillance infrastructure of staggering proportions. The connection to the narrative of the three-eyed atlas lies in an intriguing parallel. Just as comets carry messages from distant star systems, encoded not in human language, but in their fundamental chemistry and isotopic ratios, humanity is now constructing systems capable of transmitting unbreakable encoded messages across our own planet. Both represent information that endures hostile environments. The chemical composition of comets surviving the rigors of interstellar space and the sun's heat, and quantum keys resisting active adversaries attempting interception. Both push the boundaries of what is achievable. Comets as natural information carriers shaped by billions of years of physical processes, and quantum networks as artificial information carriers engineered over decades of scientific endeavor. Numerous uncertainties persist. Current quantum key distribution rates, typically measured in kilobits per second, significantly lag behind classical communication speeds, which are measured in gigabits or terabits per second. Scaling quantum networks to accommodate internet-level traffic will necessitate either substantial improvements in photon transmission and detection efficiency, or the development of fundamentally novel approaches to quantum networking. Decoherence, the degradation of quantum properties due to environmental interactions, imposes intrinsic limitations on the duration for which quantum states can be maintained and the distances over which they can be transmitted. Satellites assist in extending range by operating in the vacuum of space, above the majority of the Earth's atmosphere. However, atmospheric turbulence encountered at ground stations continues to impair performance. Endpoint security presents another significant challenge. Quantum key distribution ensures the secure transmission of keys, but these keys must ultimately be utilized by classical computers to encrypt and decrypt data. If these computers are compromised through malware, unauthorized physical access, or side-channel attacks that monitor electromagnetic emissions or power consumption, then the supposedly unbreakable quantum keys become rendered irrelevant. Security is invariably as robust as its weakest link, and in any practical system, such weak links are numerous. The narrative of the quantum space race encapsulates a fundamental aspect of human nature and technological progression. We engage in competition, even in the pursuit of understanding and harnessing the very foundational laws of physics. Quantum mechanics, arguably the most successful physical theory ever devised in terms of its predictive accuracy and technological impact, is now becoming a focal point of geopolitical rivalry. The same quantum principles that elucidate atomic structure and chemical bonds are now being employed to secure communications and hold the promise of revolutionary computing power. Nations are investing billions in quantum research, not merely out of pure scientific curiosity, but because quantum technology may well determine the balance of military power and economic leadership in the coming decades. Whether this competitive drive will accelerate innovation more effectively than collaborative efforts, and whether the benefits of quantum networks will be shared globally or concentrated among a select few technologically advanced nations, remain open questions as this race intensifies. Part 9. The circular economy within you. Science occasionally yields discoveries so astonishing, so counterintuitive, that they compel us to reevaluate our fundamental assumptions about what is possible. The recent announcement that synthetic biologists have successfully engineered yeast to transform human urine into hydroxyapatite, a bone mineral, represents one such groundbreaking revelation. The potential applications span the medical and ecological domains, and the deeper implications touch upon the intrinsic value of waste and the surprising adaptability of biological systems when reprogrammed to transmute one substance into another. Urea, the primary nitrogen-containing compound in urine, functions as a waste product of mammalian metabolism. When proteins undergo breakdown within the body, amino acids are metabolized, and the nitrogen they contain must be excreted. Aquatic organisms directly excrete ammonia, a straightforward and energetically inexpensive solution when living in water, which dilutes and carries away the toxic compound. Terrestrial animals, however, face a different challenge. While ammonia is highly toxic if it accumulates, water conservation is paramount. Consequently, land animals have evolved more complex strategies. Birds and reptiles produce uric acid, a relatively insoluble compound that precipitates and can be excreted as a paste, thereby minimizing water loss. Mammals, on the other hand, produce urea, which is sufficiently soluble for transport in water, but is less toxic than ammonia, and is excreted in liquid urine, representing a compromise between water conservation and waste elimination. Humans generate approximately 1 to 2 liters of urine daily, depending on fluid intake and metabolic rate, containing roughly 20 to 30 grams of urea. This translates to approximately 10 kilograms of urea per person annually. When multiplied by the global population of 8 billion people, this amounts to an estimated 80 million metric tons of urea excreted each year. Currently, this urea typically enters sewage systems, where it is either broken down by bacteria or released into the environment. The novel synthetic biology approach poses the question, could this waste stream be repurposed into something of value? Hydroxyapatite constitutes the mineral component of bones and teeth, a calcium phosphate compound with the chemical formula Ca10PO4,6OH2. It imparts the rigidity and structural integrity that enables bones to support body weight and protect vital organs. Natural bone is a composite material, featuring hydroxyapatite crystals embedded within a collagen protein matrix, thereby combining the hardness of the mineral with the flexibility and resilience of organic fibers. Medical applications necessitate the use of pure hydroxyapatite for bone grafts, dental implants, and reconstructive surgical procedures. Currently, hydroxyapatite is synthesized through chemical processes or harvested from animal bones. Both of these methods have limitations concerning purity, crystal structure, and production costs. The engineered yeast methodology operates through metabolic pathway engineering. Researchers identified the requisite series of enzymatic reactions needed to convert urea into the chemical precursors of hydroxyapatite and subsequently inserted genes encoding these enzymes into yeast cells. The yeast, Saccharomyces cerevisiae, commonly employed in brewing and baking, now possesses synthetic metabolic pathways that are not found in nature. When provided with urine as a nitrogen source and supplemented with calcium and phosphate ions, these yeast cells produce hydroxyapatite crystals that precipitate out and can be harvested. The underlying mechanism involves multiple stages. The enzyme urease breaks down urea into ammonia and carbon dioxide. The ammonia is then incorporated into amino acid synthesis pathways, while the carbon dioxide, along with additional calcium and phosphate ions, undergoes mineralization reactions that yield hydroxyapatite. The precise crystallographic characteristics of the resulting product, including the size, shape, and purity of the hydroxyapatite crystals, are contingent upon the reaction conditions, such as pH, temperature, ion concentrations, and the genetic programming of the yeast pathways. Initial findings show considerable promise, producing hydroxyapatite with properties akin to bone mineral. However, significant optimization efforts are still required before the process becomes practically viable for medical applications. Current efficiency and yield rates impose limitations on immediate implementation. The yeast produces hydroxyapatite at concentrations too low for commercial viability, necessitating the use of large bioreactor volumes to generate substantial quantities. Purification challenges arise because the hydroxyapatite must be meticulously separated from the yeast cells, components of the growth medium, and other metabolic byproducts. Purity is of paramount importance for medical use. The presence of foreign proteins or bacterial endotoxins within implanted hydroxyapatite could trigger adverse immune responses or infections. Achieving medical-grade purity from a biological production system demands stringent quality control and purification protocols. Nevertheless, the potential of this technology is transformative. Bone fractures affect millions of individuals annually. While most heal naturally, complex fractures or bone loss resulting from disease or trauma often necessitate grafts or synthetic materials to facilitate healing. Existing bone graft materials include autografts, harvested from the patient's own body, allografts, sourced from cadavers, and synthetic ceramics. Each of these options presents its own set of drawbacks. Autografts require an additional surgical procedure for tissue harvesting. Allografts carry a minor risk of disease transmission and immune rejection. Synthetic ceramics sometimes fail to integrate effectively with natural bone tissue. Hydroxyapatite produced biologically from waste materials could offer an abundant and cost-effective alternative, provided that the challenges related to production and purification are successfully addressed. Dental implants represent another significant market. Hydroxyapatite coatings applied to titanium implants enhance osseointegration, the process by which the implant bonds with the jawbone. Current coating techniques employ hydroxyapatite produced through high-temperature chemical processes, which are energy-intensive. Biological production at ambient temperature in an aqueous solution would reduce energy costs and the associated carbon footprint, while potentially yielding crystal structures that more closely resemble natural bone and thus integrate better with living tissue. The ecological benefits extend beyond the direct utilization of the manufactured material. Urea present in wastewater contributes to eutrophication when discharged into rivers and coastal waters. Excess nitrogen stimulates algal blooms, which in turn deplete dissolved oxygen levels and create hypoxic dead zones. By capturing urea and converting it into a solid mineral, nitrogen is effectively removed from the waste stream, thereby mitigating environmental impact. This process embodies the principle of waste valorization, treating waste as a valuable resource rather than simply a disposal problem. Controversies are inevitably associated with the use of human waste in the production of medical materials. Deep-seated cultural taboos surround urine and feces, even though we intellectually understand that purified compounds possess no inherent memory of their origin. The calcium atoms present in hydroxyapatite derived from urine are chemically identical to those from any other source. Once purified, the material bears no trace of its waste origin beyond the historical fact of its production pathway. Yet, psychological resistance persists. Would patients readily accept bone grafts or dental implants produced from urine? Would regulatory bodies approve such materials for human consumption? These questions delve more into cultural values and risk perception than into technical feasibility. Applications for astronauts may present the most compelling use case. Mars colonists or crews undertaking long-duration space missions will face severe resource constraints, making every recycling opportunity invaluable. Crew members will inevitably produce urine daily, and this urine contains nitrogen and other essential elements that must be processed, either through recycling or disposal. Converting urine into usable hydroxyapatite for medical purposes or construction materials would effectively address two critical needs simultaneously: waste management and the production of essential resources. The closed-loop life support systems essential for space exploration necessitate a strong emphasis on maximizing recycling and minimizing waste. Your biological waste could literally be a lifesaver, particularly if a bone fracture on Mars necessitates a graft, and the sole source of hydroxyapatite available originates from recycled crew urine. The significant resistance encountered from major agricultural corporations concerning the adoption of circular biotechnologies appears to stem from anticipated rather than proven conspiracies. Corporations in the pharmaceutical and medical device sectors derive their revenue from current manufacturing processes and established distribution networks. Innovative technologies that challenge established business paradigms invariably face opposition, irrespective of their technological sophistication. Whether this opposition materializes for urine-derived hydroxyapatite will hinge on factors such as production expenses, the potential for large-scale manufacturing, the complexity of regulatory approval pathways, and the intellectual property landscape. If the technology can be patented and subsequently controlled by established entities, its widespread adoption becomes more probable. Conversely, if it poses a threat to the high profit margins of a particular product, resistance is more likely to intensify. The underlying lesson extends beyond this specific application. Nature operates on a principle of absolute efficiency, with no waste. Nutrients continuously circulate through ecosystems. The byproducts of one organism serve as sustenance for another. Energy flows unimpeded, and elements undergo perpetual cycles. Humanity originally existed in societies where waste management was uncomplicated, owing to sparse populations and natural processes adept at breaking down and repurposing most discarded materials. The advent of industrialization and urban development disrupted these natural cycles, generating waste streams that have overwhelmed the Earth's capacity for natural recycling. Synthetic biology offers the means to artificially re-establish these vital cycles by engineering organisms to fulfill ecological roles that do not naturally exist but are crucial for human needs. The transformation of urine into bone mineral is merely one illustration. The same principles can be applied to converting carbon dioxide into fuel, plastic refuse into biodegradable polymers, and agricultural runoff into valuable chemical compounds. We are actively learning to reintegrate the closed loops that our technological progress had previously disrupted, effectively catching up to the circular economy that nature has perfected over billions of years. Part 10. The Universal Yawn. Observing animal behavior offers boundless fascination because it mirrors cognitive and emotional states familiar to us from our own experiences, yet it is displayed by creatures whose internal worlds remain enigmatic. Contagious yawning, the phenomenon where observing another individual yawn prompts an involuntary urge to do the same, was believed until recently to be confined to humans and a select few highly social mammals such as chimpanzees and canines. However, the release of a study detailing contagious yawning in zebrafish challenges this long-held assumption and raises perplexing questions about the evolutionary origins and neurological underpinnings of this behavior. Zebrafish, small freshwater fish indigenous to the rivers of South Asia and popular subjects in scientific research, as well as common additions to home aquariums, have become exemplary model organisms for investigating vertebrate development and behavior. Their embryos possess a transparency that allows researchers to observe organ formation in real time under microscopic magnification. Their genetic makeup is thoroughly documented, with established tools available for gene manipulation and the observation of resulting effects. Furthermore, their diminutive size, low maintenance costs, and prolific offspring production make them exceptionally well suited for extensive experimental undertakings. Yet, no one anticipated their participation in contagious yawning. The experimental design involved housing zebrafish in adjoining tanks, enabling visual interaction through transparent partitions. Yawning was artificially induced in one fish by temporarily reducing oxygen levels, a recognized stimulus for yawning across numerous species. Cameras meticulously recorded the actions of both the yawning fish and its observing counterparts. Subsequent analysis indicated that the observer fish exhibited a statistically significant increase in yawning frequency after witnessing a neighboring fish yawn, with temporal correlations suggesting genuine contagion rather than coincidental yawning triggered by shared environmental stimuli. The startling nature of this discovery arises from the prevailing belief that contagious yawning necessitates the presence of mirror neurons or analogous neural circuitry, which facilitates an organism's capacity to mentally simulate the actions and internal states of others. These neural pathways, concentrated in primate brains and hypothesized to exist in certain social mammals, form the neurological foundation for empathy, observational learning, and the ability to comprehend the mental states of others. Fish brains, in contrast, lack the distinct cortical structures that house mammalian mirror neurons. Their neurological organization is fundamentally different, possessing a simpler structure in certain aspects, though by no means simplistic overall. The presence of contagious yawning in zebrafish implies either that this behavior does not require the sophisticated neural mechanisms previously believed essential, or that convergent evolution has independently generated similar neural circuits in fish through entirely distinct anatomical routes. The precise neural pathways governing yawning in any species remain incompletely understood. The act itself involves the coordinated contraction of muscles in the jaw, face, throat, and respiratory system, resulting in the characteristic wide opening of the mouth, a deep inhalation, followed by a slower exhalation. The behavior appears to be involuntary once initiated, resisting conscious suppression, even in social contexts where yawning might be considered inappropriate. A variety of stimuli can trigger yawning, including fatigue, boredom, low oxygen levels, and the visual cue of another individual yawning. The diversity of triggers suggests multiple neural pathways converging on a common motor response. In humans, contagious yawning escalates during childhood development, peaks in young adulthood, and demonstrates a correlation with empathy metrics. Individuals who score highly on empathy questionnaires are more prone to yawning when observing others. Conversely, individuals diagnosed with autism spectrum disorders, who often experience challenges in social cognition and empathy, exhibit a reduced propensity for contagious yawning. These observed correlations bolster the hypothesis that contagious yawning is dependent on neural systems involved in social understanding and emotional attunement. Discovering this same behavior in zebrafish, creatures not typically associated with empathy or complex social cognition, disrupts this neatly constructed narrative. The evolutionary enigma deepens when considering the distribution of this trait across different taxonomic groups. Contagious yawning is observed in humans, chimpanzees, bonobos, dogs, and now, zebrafish. It appears to be absent or has not yet been demonstrated in numerous tested species, including cats, horses, and most avian species. This fragmented distribution across the animal kingdom suggests either multiple independent evolutionary origins for the behavior or an ancient origin from which it was subsequently lost in many lineages. Neither explanation is entirely satisfactory. The independent evolution of something as specific as contagious yawning in mammals and fish seems improbable unless the behavior serves a crucial function that we have yet to identify. An ancient origin necessitates an explanation for why so many species subsequently lost this trait. Hypotheses regarding its function vary considerably. One proposal posits that contagious yawning facilitates group coordination by synchronizing arousal or attentional states within social groups. If a single individual detects an environmental shift that elicits yawning, perhaps signaling a transition from vigilance to rest, the propagation of this signal throughout the group could aid in coordinating collective behavior. Fish schools undoubtedly require coordination. They move in unison, executing synchronized turns, maintaining precise spacing, and responding to perceived threats with coordinated evasive maneuvers. Could contagious yawning be an integral component of the behavioral repertoire that enables this coordination? Another hypothesis centers on stress reduction and social bonding. Yawning may serve to regulate stress hormones or recalibrate neural states during periods of social tension. Witnessing others yawn and reciprocating the action could create a feedback loop that assists groups in collectively managing stress. Zebrafish are gregarious animals that form schools in their natural habitat, and their social dynamics involve dominance hierarchies, competition for mates, and vigilance against predators. It is conceivable that contagious yawning plays a role in preserving group cohesion under stressful conditions. The ongoing debate revolves around whether the behavior observed in zebrafish can genuinely be classified as yawning, or if it represents a different jaw movement or gill action that has been misidentified. In typical circumstances, fish do not respire air, meaning the respiratory component of mammalian yawning lacks a direct equivalent. The gaping mouth movement observed in zebrafish could serve distinct physiological purposes related to gill ventilation or feeding. Critics argue that without conclusive evidence demonstrating that the fish behavior shares the same neural triggers and physiological outcomes as mammalian yawning, classifying it as contagious yawning anthropomorphizes a behavior that, while superficially similar, is functionally divergent. Proponents, however, contend that the behavior exhibits key characteristics of mammalian yawning, including its involuntary nature, a stereotyped motor pattern, and triggers such as hypoxia and, as now demonstrated, social contagion. While the neural pathways may differ between fish and mammals, separated by hundreds of millions of years of evolutionary divergence, if the behavior serves analogous functions and responds to similar stimuli, the designation of yawning remains appropriate. Biology is replete with instances of convergent evolution, where distinct structures fulfill similar functions. Bird wings and bat wings, though anatomically different, are functionally equivalent. It is plausible that zebrafish yawning and mammalian yawning represent convergent solutions to comparable behavioral or physiological challenges. Speculation extends into more profound biological territories. Could yawn contagion represent a universal signal? An ancient communication channel that predates more sophisticated social cognition? It is possible that the fundamental neural circuitry enabling contagious yawning evolved early in vertebrate history, persisting across hundreds of millions of years because it serves essential coordination functions in social species. This scenario would imply that the behavior offers significant fitness advantages, enhancing survival or reproductive success to a degree that natural selection favors its preservation despite the neural machinery required. A more speculative, though rarely articulated in academic discourse, possibility whispered in conference corridors ponders whether phenomena of synchronization might extend beyond individual species, perhaps even across entire biological kingdoms. Yawn contagion, as currently understood, operates through sensory perception. The act of seeing or hearing someone yawn triggers neural pathways that subsequently induce yawning. However, broader synchronization in nature occurs through mechanisms that we are only beginning to comprehend. Heart cells in culture synchronize their beating rhythms through electrical and chemical signaling. Fireflies in Southeast Asian mangrove ecosystems synchronize their flashing patterns across hundreds of individuals. Could there be fundamental biological principles of synchrony and resonance that manifest in yawn contagion, among other phenomena? The narrative's connection to cosmic themes is established through the concept of resonance and synchronization across various scales. Fish schools move as coordinated entities, responding to each other's movements via lateral line sensors that detect changes in water pressure. Flocks of birds execute synchronized turns, with each individual adhering to simple rules governing spacing and alignment, resulting in complex emergent patterns. On a larger scale, planets orbit in resonant patterns, with gravitational interactions locking their orbital periods into precise integer ratios. Jupiter's moons, Europa, Ganymede, and Io, orbit in a 4:2:1 resonance, with each orbital configuration repeating predictably. At cosmic scales, galaxy clusters engage in gravitational interactions, their dynamics coupled across millions of light years. Synchronization appears to be a foundational principle that governs systems from the molecular to the cosmic level. Oscillators, whether they be neurons firing, hearts beating, pendulums swinging, or planets orbiting, tend to synchronize their phases when coupled, their rhythms and frequencies aligning to common frequencies. The mathematical principles governing coupled oscillators reveal surprising commonalities across vastly different physical systems. It is conceivable that yawn contagion represents a biological manifestation of these universal principles of synchronization, a form of social oscillator that couples through observation and triggers synchronized responses. Human brains and celestial bodies may share more commonalities than is immediately apparent if one shifts their perspective from specific mechanisms to abstract principles. Both are intricate dynamical systems possessing internal structure, emergent properties, and couplings with their external environments. Both process information, albeit through radically different mechanisms and at vastly disparate scales. Brains process sensory inputs and generate behavioral outputs through electrochemical signaling across neural networks. Stars process gravitational inputs and generate radiation outputs through nuclear fusion, regulated by hydrostatic and thermal equilibrium. While the analogy rapidly loses its utility if pushed too far, it nonetheless points towards profound questions concerning complexity, information, and organization within the universe. The zebrafish study, at its core, serves as a potent reminder of our limited understanding of animal minds and behaviors. Every assumption, every fact previously considered established regarding animal capabilities remains provisional and subject to revision upon the emergence of new evidence. We once believed contagious yawning to be contingent on empathy and mirror neurons. Apparently, fish did not receive this memo. What other behaviors we deem exclusively human or mammalian might possess deeper evolutionary roots or a wider distribution than we currently realize? Tool use, for instance, is observed in birds and octopuses. Culture, defined as learned behaviors transmitted socially across generations, exists among whales and crows. Metacognition, the capacity for self-reflection on one's own thought processes, shows indications in rats and dolphins. The more we investigate, the more apparent it becomes that the distinctions we draw between humans and other animals, and between complex and simple minds, blur under careful scrutiny. Part 11. The celestial body that will graze Earth's atmosphere. April 13th, 2029, will be a date etched in human memory, assuming humanity persists to recall it. On this day, asteroid 99942 Apophis, named after the ancient Egyptian deity of chaos and darkness, will traverse Earth's vicinity at an altitude of 31,000 kilometers. To provide perspective, geostationary satellites orbit at approximately 35,000 kilometers. Apophis will pass within the orbital path of satellites crucial for weather forecasting, global communications, and GPS navigation. It will be readily visible to the naked eye, appearing as a swiftly moving point of light against the backdrop of stars. This marks the first instance in recorded history where an asteroid of this magnitude will approach Earth so closely that casual observers can witness its passage. Current orbital trajectory calculations indicate no immediate risk of impact. The close approach is confirmed, and the celestial mechanics are well understood. However, the asteroid's path will carry Apophis safely past our planet without collision. This certainty is the culmination of decades of meticulous observation and orbital refinement. When Apophis was first identified in 2004, initial trajectory estimations could not entirely dismiss a small, yet non-zero, probability of impact during its 2029 flyby. This announcement briefly generated public apprehension and spurred intensive scientific inquiry. Subsequent observations, as the asteroid became visible in different segments of its orbit, allowed for more precise calculations, narrowing the uncertainty ellipse, the region where the asteroid might be located at any given moment, until the possibility of a 2029 impact was definitively eliminated. However, the narrative does not conclude in 2029. The close proximity of this passage will alter Apophis's orbit due to gravitational interactions with Earth. When an asteroid passes near a planet, tidal forces and gravitational acceleration can significantly modify its trajectory, sometimes with dramatic consequences. The extent of this alteration is contingent upon the closeness of the approach and the relative velocities involved. Apophis will experience a substantial orbital deflection, modifying its orbital period around the Sun and influencing its future potential for Earth-crossing trajectories. Predictions for subsequent close approaches in 2036 and 2068 carry greater uncertainty because these future positions are dependent on the precise details of the 2029 encounter, details that cannot be measured with absolute accuracy until the encounter itself has occurred. The proximity, closer than geostationary orbit, presents an unparalleled scientific opportunity. Telescopes will continuously monitor Apophis as it approaches, enabling the measurement of its rotational state, the mapping of its surface features, the determination of its composition through spectroscopic analysis, and the precise measurement of its size and shape using radar. The asteroid is approximately 370 meters in diameter, substantial enough to inflict regional devastation should it ever impact, yet small enough that discerning surface details from Earth-based observations remains a considerable challenge. The close passage brings it within the effective range of techniques typically reserved for near-Earth objects during even closer approaches. Radar astronomy will play a pivotal role. Radio telescopes, such as the Goldstone antenna in California and the Arecibo replacement facility, assuming its operational status by that time, can transmit radio waves toward asteroid surfaces and analyze the returning echoes. Radar provides highly accurate distance measurements, precise to within meters, rotation period measurements accurate to seconds, and surface roughness data that optical telescopes cannot match. Delay Doppler radar imaging generates two-dimensional representations where one axis indicates distance, determined by the echo's time delay, and the other axis represents velocity, derived from the Doppler shift of the echo. These radar images reveal the object's shape, rotation, and surface topography, sometimes detecting boulders, craters, and ridges mere meters in dimension. Studying the rotation is significant because asteroids spin, and their spin states offer insights into their history. Apophis rotates with a period of approximately 30 hours, determined from light curve analysis, which tracks variations in its brightness as different facets reflect sunlight towards Earth. This rotation rate is currently stable, but the 2029 Earth encounter is expected to alter it. Tidal forces exerted on the asteroid during its passage by Earth will influence its rotation, potentially accelerating or decelerating it depending on the geometric configuration. Measuring this change in rotation will provide valuable data regarding the asteroid's internal structure, indicating whether it is a solid monolithic body or a loosely bound aggregation of smaller fragments held together by gravity. The Yarkovsky effect introduces an additional layer of complexity. Asteroids absorb solar radiation, warming their surfaces, and subsequently re-emit this energy as infrared heat. This thermal radiation carries momentum, creating a subtle but persistent thrust that nudges the asteroid. For a rotating asteroid, the side experiencing afternoon is warmer than the side experiencing morning, and this asymmetrical thermal emission generates a minor but continuous force that either accelerates or decelerates the asteroid in its orbit, depending on whether its rotation is prograde or retrograde. Over millions of years, the Yarkovsky effect can significantly alter an asteroid's orbit, potentially displacing objects from the main asteroid belt into Earth-crossing trajectories. For Apophis, precisely measuring the Yarkovsky effect is crucial for predicting its long-term orbital evolution. The effect is exceedingly small, resulting in orbital changes of only meters per year, but these incremental shifts accumulate over decades, leading to uncertainties of kilometers in positional predictions. The 2029 close approach offers a unique opportunity to quantify the Yarkovsky acceleration by comparing the asteroid's actual position against predictions that do not account for thermal effects. Any observed discrepancy would indicate the influence of the Yarkovsky effect, allowing for the calibration of models used to forecast future encounters. Public perception presents both a challenge and an opportunity. Apophis has frequently appeared in news headlines since its discovery, typically accompanied by alarmist language concerning killer asteroids and cosmic threats. The actual risk is demonstrably low to negligible for all encounters calculated to date, yet communicating risk effectively is inherently difficult. Explaining that there exists a 1 in 45,000 probability of impact in 2068 conveys different meanings to different individuals. Statisticians perceive this as a negligible risk, far below numerous risks we routinely accept. However, to someone unfamiliar with probabilistic concepts, 1 in 45,000 might sound concerning, implying a genuine possibility rather than an event of exceedingly low probability. Proposals for missions targeting Apophis have circulated within the planetary defense community. Dispatching a spacecraft to rendezvous with the asteroid during or shortly after its 2029 Earth flyby would yield close-up data unattainable from Earth-based observations. Such a mission could meticulously characterize the asteroid's composition, internal structure, and surface properties in unparalleled detail. This endeavor could also serve as a tangible display of deflection technologies, employing methodologies such as kinetic impact or gravity tractors to subtly adjust Apophis' orbital path, thereby substantiating our capacity to safeguard Earth from future extraterrestrial projectile threats. NASA's DART mission, the Double Asteroid Redirection Test, achieved a successful impact with the asteroid Dorphos in the year 2022, validating the principle of kinetic deflection as predicted. The impact effectively altered Dorphos' trajectory around its larger celestial companion, Didymos, thereby demonstrating that humanity possesses the ability to modify asteroid paths, provided adequate advance notice is available. The Apophis mission would build upon the achievements of the DART mission, investigating deflection techniques on a more substantial object, one that holds greater scientific fascination. The emergence of conspiracy theories suggesting NASA is deliberately downplaying impact probabilities is both predictable and baseless, though psychologically comprehensible. Space agencies navigate a delicate equilibrium between maintaining openness and preventing public alarm. Disseminating every preliminary orbital calculation, complete with its inherent uncertainties, can incite apprehension when those uncertainties are substantial. Although such broad uncertainties are commonplace for newly identified celestial bodies with limited observational data, withholding announcements until calculations are refined risks accusations of concealment, particularly if an independent discovery occurs or sensitive information is leaked. Space agencies, including NASA, have generally moved toward greater transparency, publishing orbital calculations and impact likelihoods through systems like Sentry and the Torino scale. However, this transparency does not eradicate conspiracy theories. It merely redirects their focus from the alleged concealment of impacts to the supposed cover-up of deflection failures or extraterrestrial involvement. The narrative framing of an asteroid that will narrowly miss Earth evokes a compelling blend of peril and wonder. These impending close encounters inspire awe. APUs will not strike our planet, but its passage will be sufficiently near for us to perceive its presence, observe its trajectory, and witness the cosmic mechanisms that periodically guide mountain-sized rocky bodies into Earth's vicinity. This close flyby serves as a potent reminder that space is not devoid of matter, that remnants from the solar system's formation continue to traverse its expanse, and that these debris fields occasionally intersect with Earth's path. While we have been remarkably fortunate thus far, such good fortune is not guaranteed indefinitely. Proactive measures are crucial. The development of detection, tracking, characterization, and deflection capabilities represents humanity's safeguard against the cosmic lottery that eventually will present an impact event. Furthermore, this event offers a global educational opportunity. The defense of our planet necessitates international collaboration. Asteroids disregard national boundaries, and a threat to any single nation constitutes a threat to all. The United Nations Committee on the Peaceful Uses of Outer Space serves as a coordinating body for international efforts to monitor near-Earth objects and develop response strategies. The close approach of APOUS in 2029 is anticipated to stimulate renewed interest in funding and policy related to planetary defense, potentially accelerating the advancement of detection networks and deflection technologies. The forthcoming celestial spectacle in 2040, often referred to as a planetary parade, provides valuable context. The universe operates on temporal scales that transcend human perception. Asteroids arrive according to the dictates of orbital mechanics. Planets align in accordance with Kepler's laws. Comets descend from the Oort cloud, propelled by gravitational disturbances that originated millennia ago. We meticulously record these cosmic occurrences on our calendars, anticipating them and preparing for them. However, their unfolding is governed by immutable physical laws, not by human convenience. A PAUS will pass by in 2029, irrespective of whether we are observing, whether we are concerned, or whether we are prepared. The cosmos's profound indifference to human affairs is simultaneously terrifying and liberating. Part 12. When Planets Dance, September the 20th, 2040. Make a note of this date on whatever calendar system endures the intervening years, for on this day, the solar system will present a geometric configuration so rare as to command attention, yet common enough that similar arrangements recur with predictable regularity. 6 planets, Mercury, Venus, Mars, Jupiter, Saturn, and Uranus, will appear within a relatively confined sector of the sky as viewed from Earth, their longitudes, or angular positions along the ecliptic, separated by less than 90 degrees. The media will undoubtedly label this a planetary alignment or parade, though technically, the planets will not form a perfectly straight line. Instead, they will simply cluster within a particular region of the sky, simultaneously visible from Earth's night side. The geometric principle at play is straightforward. Planets orbit the Sun in roughly the same plane, known as the ecliptic, which is defined by Earth's orbital plane. From our vantage point, planets appear to traverse the sky along a path that follows the constellations of the zodiac. At times, planets are distributed around the entire ecliptic, visible at different moments as Earth rotates. At other times, their orbital positions converge, causing multiple planets to appear in the same sky region concurrently. These clustering events occur regularly, though not with strict periodicity. They are the result of planets possessing distinct orbital periods, occasionally aligning their positions. The degree of rarity depends on the number of planets we stipulate to be involved and the precision with which we define an alignment. Arranging all 8 planets within a 90-degree band occurs approximately every few decades. Confining them to a 30-degree span happens every few centuries. Achieving a perfect straight line with all planets at 0-degree separation, as viewed from the Sun, is likely beyond the scope of human timescales, as their orbital periods do not share exact integer ratios that would facilitate perfectly recurring alignments. The event in 2040 is expected to be particularly favorable for observation because the planetary cluster will include bright planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn, all easily observable without optical assistance. Uranus will also be present, though it will require binoculars or small telescopes. Neptune, however, will be situated elsewhere in its orbit and will not participate in this gathering. The planets will be visible in the evening sky after sunset, rising together in the east and tracing an arc across the southern sky, offering several hours of viewing opportunities depending on the observer's latitude. Amateur astronomers are anticipating a field day. Capturing all visible planets within a single wide-angle photograph will become feasible during these events, yielding images that beautifully illustrate the architecture of the solar system. The varying brightnesses and colors of the planets will provide considerable visual interest. Venus will appear brilliantly white, Mars a distinct orange-red, Jupiter a yellowish-white, Saturn similar to Jupiter but slightly dimmer, and Uranus a faint pale blue-green disk, even through binoculars. Photographing them collectively will create a composite portrait of planetary diversity compressed into a single frame. Professional astronomers will also find opportunities beyond aesthetically pleasing images. While planetary alignments do not create any unique gravitational effects, despite persistent myths about tidal forces or seismic triggers, they do offer chances to conduct simultaneous measurements across multiple planets using identical instruments and methodologies. Comparative planetology stands to benefit from such occasions. Measuring atmospheric characteristics of Venus, Jupiter, and Saturn within the same observational window allows for the control of instrumental and observational variables, leading to more reliable comparisons. The alignment might also present opportunities for the detection of unusual celestial objects. When planets converge, the background star field in that region receives more intense scrutiny than usual. Faint asteroids, distant comets, or even undiscovered planets in the outer solar system could be spotted by observers scanning the area for planets. The hypothetical Planet 9, proposed to explain the orbital clustering of distant trans-Neptunian objects, remains elusive despite ongoing searches. If it exists, its predicted location drifts slowly through the zodiac, and it may happen to be situated near the region of planetary clustering in 2040, thus increasing its chances of detection simply because more telescopes will be directed toward that vicinity. Throughout human history, mythological and cultural narratives have surrounded planetary alignments. Ancient astronomers meticulously charted planetary positions, noting conjunctions and alignments, and attributing significant meaning to these celestial events. Astrological traditions, which persist despite a lack of scientific validation, ascribe symbolic significance to planetary configurations based on symbolism and perceived correlations. The scientific worldview dismisses these associations as instances of pattern recognition applied to random coincidences. Nevertheless, the human psychological response to celestial alignments remains profound. When planets congregate in a particular sky sector, it evokes a sense of significance, even if we intellectually understand it to be merely a product of orbital geometry. Certain fringe groups will inevitably forecast dire consequences stemming from the 2040 alignment. The notion of planetary gravitational forces supposedly triggering earthquakes or weather calamities represents a recurring doomsday scenario unsupported by physical principles. The gravitational influence of planets on Earth is minuscule compared to that of the Moon and the Sun. Even when planets align, their combined gravitational pull exerts infinitesimally small perturbations on Earth's orbit that have no measurable impact on geological or atmospheric processes. However, factual accuracy does not preclude prediction. Online, somewhere, individuals will assert that the alignment will instigate disasters, and others will lend credence to these claims and make preparations. When these predicted disasters fail to materialize, the predictions will be quietly disregarded or rationalized away. Within these alignments lie hidden scientific opportunities, such as the measurement of mass distribution within the solar system. Precise tracking of planetary positions enables testing of gravitational theories and refinement of planetary mass estimations. Every planet exerts a gravitational influence on every other planet, resulting in orbital perturbations that accumulate over time. By accurately measuring planetary locations and comparing them to their predicted positions based on Newtonian gravity, astronomers can identify anomalies that might suggest the presence of unknown masses elsewhere in the solar system, or, more speculatively, deviations from gravitational theory itself. The cultural dimension of alignments as global events holds significance in an increasingly interconnected world. Unlike eclipses, which are observable only from specific geographical locations, planetary configurations are visible worldwide, weather permitting. This fosters shared experiences that transcend cultures and continents. In 2040, individuals in Tokyo, New York, Sydney, and Lagos will witness the same celestial arrangement, creating a moment of cosmic commonality that transcends political and cultural divides. The analogy to a planetary choir serves metaphorically. Each planet traverses its orbit at its own unique pace. Mercury races around the Sun in just 88 days, while Neptune ambles along, taking 165 years to complete a single orbit. These disparate periods generate complex rhythms and patterns over extended durations. When planets cluster, it is akin to a moment in a protracted cosmic symphony where multiple instruments sound in unison, creating a harmonious chord before gradually drifting apart once more into their individual melodic lines. This metaphor should not be overextended, as planets do not literally produce sounds or generate music, but it effectively conveys the essence of patterns and rhythms inherent in orbital dynamics. The foreshadowing of the 2015 supermoon serves to establish continuity within the narrative. Such alignment events and close celestial approaches mark the passage of time in ways that extend beyond individual human lifespans. An individual born in 2040 will be 12 years old when the supermoon occurs, will reach the age of 20 when a Paus makes its close approach, and will be middle-aged before the next significant planetary alignment transpires. These cosmic occurrences serve as markers within generational memory, shared experiences that define epochs and lend structure to historical time, transcending human constructs such as decades and centuries. Part 13. The Moon That Touches Earth. November the 9th, 2022, will witness the closest lunar approach of the 21st century, a supermoon so exceptional that it stretches the very definition of the term. The moon's orbit around Earth is not perfectly circular, but elliptical, meaning the Earth-Moon distance fluctuates between approximately 363,000 kilometers at perigee, the point of closest approach, and around 405,000 kilometers at apogee, the farthest distance. This variation in distance causes the moon's apparent size, as seen from Earth, to change. When the moon reaches perigee during its full phase, appearing at its largest and brightest, we designate it a supermoon. The supermoon of November 2022 will occur at an exceptionally close perigee, bringing the moon to a distance of approximately 356,500 kilometers from Earth's center. This distance is roughly 3% closer than typical supermoons and about 6% closer than average full moons. While the percentage difference in distance might seem trivial, it is crucial to remember that we are comparing angular sizes, which are affected by distance in non-linear ways. A 6% reduction in distance results in approximately a 13% increase in apparent diameter and about a 30% increase in apparent brightness. The moon's size at this closest approach will be sufficiently large that the difference in size compared to average full moons will be noticeable even without optical aids. Placing a photograph of the full moon from 2022 next to one taken at an average lunar distance will reveal an obvious disparity. The supermoon will occupy a greater portion of the sky, its features will appear larger, and its brightness will illuminate landscapes with increased dramatic effect. Under optimal atmospheric conditions, with the moon positioned near the horizon, the combined effect of its actual size increase and the moon illusion, the psychological phenomenon that makes horizon moons seem larger than overhead moons, will create vistas that appear almost surreal. Photographic opportunities will be extraordinary. Lunar photographers eagerly await supermoons to capture the moon in conjunction with landscape features, utilizing its enhanced size to craft dramatic compositions. The event in 2022 will provide the ultimate opportunity for this generation of photographers. Planning will commence years in advance, involving scouting locations where the moon will rise or set behind captivating foreground subjects, and calculating the precise timing and positioning required to achieve the desired shot. The augmentation in brightness carries implications extending beyond mere aesthetics. Moonlight, in general, is sufficiently intense to cast shadows and influence the behavior of nocturnal animals. Supermoonlight is even brighter, potentially casting distinct shadows from objects and illuminating landscapes to levels approaching those of twilight. Nocturnal creatures that synchronize their activities with lunar phases may respond to this unusual luminosity. Predators that rely on vision for hunting might gain an advantage over prey species that depend on darkness for concealment. Conversely, prey animals might modify their behavior, opting to remain hidden during the hours of peak brightness. Extreme tides represent the most significant physical consequence of close lunar approaches. Ocean tides are a result of gravitational gradients, the difference in the moon's gravitational pull on the near side of Earth compared to the far side. This gradient generates two tidal bulges, one facing the moon and another on the opposite side. Earth's rotation then carries coastlines through these bulges, producing the familiar twice-daily tidal cycle. The intensity of tides is contingent upon the moon's distance, with closer moons inducing stronger gradients and consequently higher tides. Spring tides, which are the highest tides occurring during new and full moon phases when the sun and moon align, will be amplified during the 2022 supermoon. Coastal regions already experiencing elevated spring tides will observe water levels several centimeters higher than usual. While this may not sound dramatic, during high tide coinciding with storms, those extra centimeters can be the decisive factor between water remaining within its channels or overtopping seawalls and inundating coastal infrastructure. Coastal flood warnings will likely be issued for vulnerable areas, particularly those already contending with rising sea levels due to climate change. Seismic coupling speculation ventures into more uncertain territory. Some researchers have investigated statistical correlations between lunar phases, tidal forces, and earthquake occurrences, seeking evidence that tidal stress on fault lines might trigger earthquakes that are already nearing their breaking point. The prevailing scientific consensus is that any such effect, if it exists at all, is negligibly small. Faults rupture when accumulated tectonic stress surpasses the friction that holds them in place. Tidal stresses are orders of magnitude weaker than tectonic stresses. Nevertheless, for fault lines already at the precipice of failure, even minute additional stresses might theoretically provide the triggering mechanism. Studies have identified weak correlations between tides and earthquakes in certain fault systems, but not in others, with effects so subtle as to be difficult to distinguish from statistical noise. The 2022 supermoon will serve as a natural experiment. If tidal triggering is a genuine and measurable phenomenon, we might anticipate a slightly elevated global earthquake rate during the days surrounding its closest approach. If the rates remain within normal parameters, it would further bolster the conclusion that tidal influences on seismicity are insignificant. The cultural response to the supermoon is expected to encompass both celebration and apprehension. Festivals and public viewing events will draw substantial crowds to dark sky locations and renowned landmarks. Lunar eclipses, when they coincide with supermoons, transform into media spectacles, attracting millions of viewers. Even without an eclipse, the record-breaking nature of the 2022 event will undoubtedly generate considerable interest. Concurrently, various doomsday predictions and apocalyptic interpretations will proliferate online, purporting that this close celestial approach portends disaster. These predictions follow predictable patterns and will be equally predictably inaccurate, yet they will briefly capture attention and instill unwarranted anxiety among individuals unfamiliar with astronomical facts. The phrase, "the night that glowed like day," represents an exaggeration, but it effectively conveys the qualitative experience of exceptionally bright moonlight. Human eyes possess the remarkable ability to adapt to darkness, with pupils dilating to capture more light and photoreceptor cells increasing their sensitivity. Under conditions of complete dark adaptation, the range of sensitivity of human vision spans many orders of magnitude. Moonlight during a typical full moon provides sufficient illumination to navigate comfortably, read large print, and perceive colors in a vague manner. Supermoon illumination intensifies this further, potentially enabling the reading of standard print and the recognition of colors with greater vividness. When combined with high atmospheric clarity and a dark surroundings, the visual experience approaches the illumination level of deep twilight. Studies of atmospheric scattering benefit from bright moonlight, as lunar illumination provides a stable light source for measuring atmospheric properties. Research groups investigating aerosols, clouds, and atmospheric chemistry sometimes utilize moonlight for calibration purposes or to extend observational periods beyond daylight hours. The supermoon offers unusually high signal levels, potentially facilitating more precise measurements or the detection of subtle effects that are normally below the threshold of detection. Citizen science projects could orchestrate global observations of the supermoon, gathering data on its apparent brightness, color, and any atmospheric effects from participants worldwide. Similar initiatives have successfully collected observations during eclipses, counted meteors, and documented aurora reports, thereby compiling data sets that complement professional observations and engage public interest in astronomy. The supermoon presents an accessible celestial target that anyone can observe and photograph, thereby lowering the barriers to participation. The transition to discussing comets that may outshine even this supermoon sets the stage for the concluding narrative elements. The moon, at its closest approach, will undoubtedly be spectacular, but it represents a recurring phenomenon, the nearest in a continuous series of supermoons that occur monthly, albeit with varying degrees of intensity. Comets, in contrast, are unpredictable wildcards, occasional visitors that can rival or even surpass the moon in brightness, but they do so rarely and without a fixed schedule. This comparison highlights the distinct nature of these cosmic phenomena, the predictable, cyclical movements of bodies locked in regular orbits versus the chaotic, punctuated appearances of comets descending from the outer darkness. Part 14, 2060, the brightest comet ever. In the year 2060, an event is anticipated that no living human has ever witnessed. The forecasts are already established, and the orbital calculations have been completed. Astronomers are eagerly anticipating an event set to redefine celestial spectacle, a phenomenon poised to eclipse anything witnessed in human history. A colossal object originating from the Oort cloud, that remote, icy shell encircling our solar system, is charting a course towards the inner regions. Its trajectory promises a close encounter with the sun, ensuring a dazzling display. This isn't merely about brightness or visibility. This visitor could shine with an intensity rivaling the moon itself, dominating the nocturnal panorama for an extended period, potentially weeks or even months. Should current projections prove accurate, this comet will stand as the astronomical highlight of the 21st century, an unparalleled, once-in-a-lifetime vista observable even during daylight, casting distinct shadows after sunset, and irrevocably altering humanity's perception of the cosmos for all who witness it. To contextualize this, consider that most comets traversing the inner solar system are faint, requiring optical aids for observation. A select few each decade achieve naked-eye visibility, appearing as nebulous smudges with modest tails. Every few decades, a particularly brilliant comet emerges, garnering significant public attention and drawing observers outdoors. Comet Hale-Bopp in 1997, visible for over 18 months, was one such marvel, discernible even from light-polluted urban environments. Prior to that, Comet West in 1976 offered a breathtaking display for early risers who ventured out before dawn. And of course, there is Halley's Comet, returning approximately every 75 to 76 years, documented by human civilization for over 2,000 years, appearing in Babylonian records, Chinese chronicles, and the Bayeux Tapestry. Yet, even Halley's Comet, at its most magnificent, is merely a bright comet. Impressive, certainly, but not sky-dominating. The comet of 2060, if it lives up to expectations, will achieve precisely that. Current modeling suggests it could reach an apparent magnitude of -10 or even -12, rendering it as luminous as a half-moon or potentially a full moon. To fully appreciate this, one must understand the logarithmic and inverted nature of the magnitude scale. The Sun registers at an apparent magnitude of -26.7, the full moon at -2.7, and Venus at its peak, brightness approximately -4.9. A brilliant comet like Hale-Bopp peaked around -1. Each incremental step represents roughly a 2.5-fold increase in light intensity. Therefore, a magnitude 10 comet isn't merely twice as bright as Hale-Bopp, it's thousands of times more luminous. What contributes to such an extraordinary celestial body? Size is a crucial factor. The nucleus of the 2060 comet is estimated to be of truly immense proportions, possibly ranging from 50 to 100 kilometers in diameter, making it one of the largest objects ever to venture into the inner solar system from the Oort cloud. For comparison, Comet Hale-Bopp's nucleus was approximately 60 kilometers across, which was already considered substantial. However, size alone is insufficient. The comet must also traverse a path sufficiently close to the sun. This proximity ensures that solar radiation vaporizes vast quantities of ice, generating a coma that can expand to exceed the size of Jupiter, and a tail that can extend for hundreds of millions of kilometers. The 2060 comet fulfills all these prerequisites. Its perihelion will bring it within approximately 0.3 astronomical units, roughly 45 million kilometers, placing it inside Mercury's orbit. At this proximity, solar heat will not only sublimate water ice, but also more volatile compounds such as carbon monoxide and carbon dioxide. Beyond the scientific implications, a more profound aspect is at play. For a fleeting interval in 2060, humanity will share a singular, unifying experience. Individuals across every nation and continent will direct their gaze skyward, observing the same celestial spectacle. A comet so brilliant it cannot be overlooked, so awe-inspiring it transcends linguistic, cultural, and political divides. The comet of 2060 will be unmissable, commanding the twilight and night skies, visible even from brightly illuminated metropolises, emitting enough light to potentially read by in darkness. This introduces a fascinating, perhaps unsettling consideration. What occurs when a light source rivaling the moon is introduced into the night sky? We understand that moonlight influences ecosystems. Nocturnal fauna adjust their behavior based on lunar phases, and predators alter their hunting patterns accordingly. Human circadian rhythms, the internal biological clocks governing sleep-wake cycles, are also sensitive to ambient light levels. Throughout human existence, the moon has been the preeminent nocturnal luminary. What are the consequences of introducing a third, equally potent variable into this dynamic? The truth is, we do not yet know. The comet will be observable for weeks, possibly months, during which time it will radiate light into the night environment at intensities Earth has not experienced from a comet in recorded history. Now, let us address the less comforting possibilities. Proximity to Earth often triggers concerns about impacts and potential catastrophes. To be unequivocal, the 2060 comet poses no threat of collision with our planet. Its orbital path is precisely determined, and it will safely pass at a distance of millions of kilometers. Nevertheless, it is not entirely without potential hazards. Comets release material as they approach the sun, including dust, small particles, and occasionally larger fragments, which disperse along their orbital path. Should Earth's orbit intersect this stream of debris after the comet has passed, the result could be a spectacular meteor shower. A more concerning, though improbable, scenario involves cometary fragmentation. Comets can break apart as they near the sun due to thermal stress, tidal forces, and outgassing pressure, all of which can compromise the structural integrity of the nucleus. If the 2060 comet were to fragment, and if one of the resulting pieces were to follow an orbit that brought it unexpectedly closer to Earth than predicted, we would face a significant challenge. While the probability of such an event is exceedingly low, it cannot be entirely dismissed. This underscores the critical importance of asteroid and comet tracking initiatives. However, it is hoped that the prevailing human response will be one of profound awe, for regardless of other factors, the 2060 comet will be a vision of unparalleled beauty, a potent reminder of the universe's capacity for creating breathtaking phenomena. For several weeks or months, conversations will invariably revolve around tail structures and coma dynamics. Children will remain awake past their bedtime to observe the comet. It will become an integral part of that generation's collective memory and cultural narrative. And when its passage concludes, as the comet arcs around the sun and commences its journey back to the outer solar system, we will be left with photographic records and cherished recollections. Yet, even as it recedes, another date on the cosmic calendar marks an equally significant milestone. Part 15, 2177, Pluto's inaugural anniversary and cosmic reflection. On February the 18th, 1930, a young astronomer named Clyde Tombaugh was meticulously examining photographic plates at the Lowell Observatory in Flagstaff, Arizona. His objective was to locate a hypothetical ninth planet, a celestial body presumed to exist beyond Neptune, which might account for minor orbital anomalies observed in the outer planets. The task was arduous, involving the painstaking comparison of photographic pairs taken days apart, searching for any discernible shift against the backdrop of fixed stars. It was then that he detected it, a minuscule point of light that had moved between exposures. Planet X, the ninth planet, Pluto. The discovery resonated globally, making headlines worldwide. Pluto held the distinction of being the first planet discovered by an American, and it captivated the public imagination in a way rarely seen with astronomical findings. The name Pluto, proposed by an 11-year-old girl in England named Venetia Burney, proved remarkably apt. It evoked the god of the underworld, fitting for a distant, dim world situated at the periphery of the solar system. For 76 years, schoolchildren were taught that the solar system comprised 9 planets, with Pluto, diminutive and enigmatic, serving as the final frontier before the vast emptiness of interstellar space. Then, in 2006, the International Astronomical Union established a revised definition of a planet. Pluto met 2 of the 3 criteria, but failed the third. It had not cleared its orbital neighborhood of other celestial debris. Consequently, under the new classification, Pluto was relegated to the status of a dwarf planet, reducing the solar system to 8 planets. This demotion elicited a surprisingly strong public outcry, reflecting a genuine affection for Pluto, the quintessential underdog world. However, a unique perspective emerges when considering the following. In 2177, precisely 247 years after its discovery, Pluto will complete its first full orbit around the Sun. It will return to the exact spatial coordinates where Clyde Tombaugh first identified it on those photographic plates. Consider the implication. Pluto's orbital period, the time required for one revolution, is 247.9 Earth years. At the time of Pluto's discovery in 1930, it had completed approximately 36% of a single orbit since the signing of the Declaration of Independence. We discovered Pluto, studied it, dispatched a spacecraft for a flyby in 2015, witnessed its reclassification and the ensuing debates, and throughout all this, Pluto had not even completed one revolution around the Sun. This offers a profound insight into temporal scales. Human lifespans, at best, rarely exceed 80 to 100 years, representing the extent of direct individual memory and experience. Our civilizations endure longer, with continuous written records extending back approximately 5,000 years. Yet, even on this grander scale, Pluto has completed only about 20 orbits. The entirety of human civilization encompasses merely 20 circuits around the Sun for this distant world. Expanding our view to the 4.5 billion year history of the solar system, Pluto has executed roughly 18 million orbits. While this figure seems substantial, it pales in comparison to Earth's 45 billion orbits within the same time frame. This temporal disparity is not exclusive to Pluto. The outer solar system operates on timescales that dwarf human comprehension. Neptune requires 165 years to orbit the Sun. Since its discovery in 1846, Neptune has completed just over a single orbit. Uranus takes 84 years, and Saturn, 29 years. These are celestial bodies that traverse the zodiac with a stately, almost imperceptible rhythm. Ancient astrologers recognized only 5 planets beyond Earth, precisely because their apparent motion across the sky was noticeable within a human lifetime. This leads to an intriguing question. What is the maximum temporal scale that humans can truly apprehend? We can intellectually grasp that the universe is 13.8 billion years old, or that the Sun formed 4.5 billion years ago. We can recite these figures, incorporate them into textbooks, and impart them to students. But do we truly internalize them? Can any human mind genuinely encompass 13 billion years of time in a manner that feels tangible? Likely not. Our innate intuition is calibrated to human lifespans, to the duration we anticipate living. Beyond a few generations, time transforms into an abstract concept. This is precisely why Pluto's first anniversary since its discovery serves as such a poignant marker. It represents a temporal scale that is just on the cusp of comprehensibility for our civilization. 247 years, spanning from 1777 to 2177, encompasses more than a century and a half into our future. This duration exceeds any individual human life and outlasts most institutions, yet remains sufficiently constrained to allow for the tracing of cultural continuity. individuals in 2177 will be able to consult records from Pluto's discovery and comprehend the efforts and significance of those astronomers. However, upon completing its initial orbit in 2177, Pluto will merely be commencing its second orbit since discovery, a journey that will itself require another 247 years. Pluto will not complete a third orbit until 2671. The individuals who will witness Pluto's second anniversary have yet to be born and will not be born for centuries. Will humanity still hold an interest in Pluto by then? Will we continue to observe the heavens, track the planets, and commemorate these cosmic milestones? I would like to believe so. Despite prevailing circumstances and acknowledging the often chaotic nature of human behavior, we have sustained astronomical observatories for centuries. We have meticulously kept records, faithfully transmitted knowledge, and built upon the discoveries of preceding generations. The very fact that we can accurately calculate Pluto's orbit and predict its position in 2177 stands as a testament to the power of accumulated knowledge and humanity's ability to collaborate across generations toward shared objectives. And speaking of extended temporal scales, consider this. When Comet C2024 S1 Atlas entered our solar system in 2024, it had embarked on a journey through interstellar space spanning millions of years. If ejected from a star system 10 light-years distant, traveling at 66 kilometers per second, its transit would have taken approximately 45,000 years. Throughout this entire odyssey, this comet remained frozen, unaltered, drifting through the void. It then spent a mere few months within our solar system, succumbed to the sun's influence, and vanished. However, understanding differs from lived experience. We can calculate Pluto's orbital path, but we cannot viscerally feel the sensation of taking 247 years to circle the sun. We can measure the sun's lifespan at 10 billion years, yet we cannot truly internalize that vast temporal expanse. We are inherently limited by our biology, our mortality, and our specific position within the fabric of space and time. When Clyde Tombaugh discovered Pluto in 1930, he was 24 years old. He passed away in 1997 at the age of 90, having lived to witness spacecraft visit every planet in the solar system and to see humans walk on the moon. Yet, he never lived to see Pluto complete a single orbit. No human alive at the time of Pluto's discovery will survive to witness its first orbital anniversary. That significant milestone will belong to individuals not yet conceived.